NSN 2025. This is the 17th edition of the Symposium. And we're very happy that we organize it and we are hosted by the University of William and Mary here in Williamsburg. So this is the first time I think that NSM is organized at Langley and we are hosted by a local university. And we hope this is, the first step to like more collaboration with a local university and maybe having more students from here and more events that are in collaboration with NASA and William and Mary. So thank you to Ifan Sun. That was so nice and, and helpful in organizing the conference. So I don't know if anyone knows, but this is like the second oldest university in the US, and it's also the alma mater of Thomas Jefferson. So that's a big deal. And we are in Williamsburg, which is an historical landmark here in the USA. So there is some information on the area in your NSM bag. There is a mini guide for Williamsburg with some information about what to do and where to eat, etc. So check it out. So we're and Alvin got married in Williamsburg, so it's also historical landmark. So yeah, we're looking forward for a very exciting program. And yeah, we kicked off the conference yesterday with the PBS Day, and today, and we're gonna have like a first keynote speaker, Darren Kofer, and we're gonna have three sessions actually. If you're improving verification status and D, and in the next 2 days, we are looking forward for other session and probably interesting discussions about the machine hybrid and different systems, runtime verification and temporal logic. So very excited about that. So this afternoon, don't miss the Best Baker Award. This is the first time that NSM does it, and it's sponsored by Springer. So thank you, Springer. And we are doing lunch, I think, from 12 to 1:30. So lunch is not provided. There is a cafeteria downstairs, or you can find information about places where to eat in your bag or with Google. So we are very excited for our keynote speaker. As I said today, Darren Coffer is going to talk about AI in the sky. So how to integrate safety AI and ML technique into aerospace software. Tomorrow we're going to go with Nina Thorlax, and she's going to talk about the language Stellar for modeling and analyzing optimization control. And the last day, we're going to have our very own Natasha Nyogi and Paul Miner talking about the history of formal methods at NASA, the present and the future. So again, thank you so much for all the people that worked for making this edition a success. Of course, Aaron and Laura Humphrey, the TC co-chair, Mariano and Cesar that organized the PBS Day, and also helped a lot with a local organization as well. Ifan Sun from University of William and Mary, that was the local organization chair. And finally, Tanner Slagle, that was our publicity chair. And these are our supporters, the University of William and Mary, Springer, AMA, Mary, and NASA. So thanks for Abigail that is supporting our logistics here from Mary. And yeah, so this is kind of an invitation. So we were planning on Thursday to have an informal metal dinner at the Precarious Beer Project. It is about 10, 12 minutes from here, Boston. So for federal regulation, we cannot offer you food or drink, but we hope you can join us and maybe talk about formal metal in an informal setting. So yeah, that's all. Enjoy the conference, and since I'm here, without further ado, let me present our first invited speaker, which is Darren Wilson. So while Aaron is setting up the presentation, let me introduce Darren. So we're very happy, and I'm very excited to introduce our first keynote speaker. So Darren, many of you know him already. He's a principal fellow at Collins Aerospace, and now she's leading the formal methods group there, and also the DARPA Approvers Program at Collins. His main interest, of course, is applying formal methods for improving the safety and security of aerospace systems. And he was member of the RTCA committee and the formal method supplement for the standard DO178C, and is currently a member of the SAA Committee G34, which is developing certification guidance for the use of ML and AI technology on board of aircraft. So, Darren, the floor is yours, and please a round of applause for our first invited speaker today.
Thanks, everybody, and great to see so many friends here in the audience. NFM is always a great opportunity to get together and see what folks are up to. So I don't actually lead the formal methods team, but I work closely with those folks. I report to some VP now, which is what happens when you're a fellow. But I'm at Collins Aerospace, used to be Rockwell Collins. There's been all kinds of mergers and things on the way. So Collins does all the cool airplane stuff within this larger company called RTX, also includes Raytheon and Pratt & Whitney. But there's researchers kind of at the corporate RTX level, but then there's a group of kind of Collins level research organization called Applied Research and Technology. That's where I am, and we have folks in Rome and Toulouse and Ireland and various places in the U.S. So AI in the sky, and it's been kind of a strange journey. I'm not an AI person by training, but have been involved in assurance activities and formal methods for many, many years, and of course, as a sort of a big concern right now. And kind of one of the main points I would like to convey to y'all in this talk is, there is a way forward here, and we don't want to go into the ditch on the one side, which is to say, oh, putting AI and machine learning technologies on an airplane, it's no big deal. It's just software, and I definitely hear and see people writing that, and it is not true. But on the other hand, it's also not impossible and not even necessarily crazy in all cases, although in some cases, maybe it might be inadvisable. But there's lots of applications, and we'll talk about some of them, where it makes a lot of sense, and we definitely have technological ways forward to make that work. Okay, but why would you want to do this in the first place? So, of course, we all know there's increasing demand for air travel, commercial, cargo, supply, high-density urban areas, all these other kind of good things that NASA's been involved with over the years. Ongoing shortage of trained pilots, many proposals for reduced crew, single pilot operations, maybe full autonomy. Who knows? These things are still sort of out there on the horizon to deal with some of these pressures to provide more automation for pilots. And this is going to require automating tasks currently done by pilots, some of which are safety critical. And many of those will be implemented using machine learning and AI technologies. But there's also many uses of AI and ML technologies that really don't have anything to do with autonomy. And they're really more about exploiting the efficiency of a neural network for approximating very complex functions. So to save computing resources on board the airplane. And a lot of the things that we're looking at right now fall into that category. Okay, so what do we mean by AI? We should always start with that. And here's one person's Venn diagram there, and the graybeards amongst the formal methods community will remind us that formal methods at one time was part of symbolic AI or good old-fashioned AI, and part of this this sphere. But mostly what we're talking about nowadays is in the category of machine learning, which just means systems where the specification consists of a large example data set. So here's a bunch of data that describes what I want the system to do that. And there's various categories of machine learning, of course. We're considering neural networks or a large category, and everything inside of this circle that I've drawn there is some kind of a neural network. Even large language models use a kind of neural network called transformers to deal with sequences. So that's kind of the scope of actually what we're interested in here, is things inside of this neural network machine learning circle. So yeah, almost all the current work to deploy something on board aircraft is looking at neural networks, and specifically neural networks trained to supervise learning. But we'll also talk about LLM applications in aviation to wrap up. So what are, just to set the context, what are some of the applications in aviation, and why might they have certification or assurance concerns? So there's this covers a spectrum from fairly low level, simple embedded systems that are providing advisory information to pilots, like what's the most efficient altitude for you to fly at right now, or there's a ROAS, there's a landing warning system that tells the pilot whether the runway that they're landing on is long enough given their current speed and altitude and flight state. You've probably seen things related to automated landing, vision-based landing, using a neural network perception system to identify runway and compute the pose of the airplane relative to the runway, and provide guidance information. There's a bunch of other things inside of the aircraft that we're looking at for monitoring pilot fatigue, and also just things related to the passenger and service parts of the airplane. Are one of the things that Collins has is an interiors business that makes all the things that you really love about airplanes, like seats and toilets and galleys, like that. But they make these very fancy high-end business class systems where they demonstrated systems where they're monitoring, is your glass of champagne empty and somebody should come and refill it, or did you drop your book, or are you trying to read, turn on the light, or tracking things in the galley, where are the supplies if somebody moves something to a different cubby hole. So there's all kinds of applications of machine learning that you probably need to think about. And then also we have part of our organization owns FlightAware, and does also all these different back-end ground-based communications for airlines. And so they use machine learning for cracking flight information, making predictions or forecasting, those kinds of things. So those are all in the category of products, kind of things that customers might interact with. But then we also have a lot of uses, as all big companies and small companies these days do, looking at our internal engineering processes. So this includes things like, coding Copilot and test generation, and generating documentation, and doing inspections as part of manufacturing processes. Verification. One of the interesting things that our group is going to present a paper at DASC this year is vision-based verification. So display verification, if you think about it, you got to run through a bunch of test cases, but somebody has to sit there and look at the display. It acts some sequence or set up some conditions and to tell you if the display is displaying the right thing. And wouldn't it be nice if you could just use a perception system and identify the things that are on the screen and see if they are the correct things. So do that, then you have to qualify that tool so you can process. So it's all kinds, there's layers on layers of machine learning in tools that are processing things that use machine learning to do display generation and things like that. And also, on the formal methods side, we, like other people, are looking at proof of systems, use AI to improve proof and analysis tools, make them easier to use. So those are all in these internal use categories that may or may not have safety considerations. Okay, so why is this even a problem? What are the challenges? I'll put it in 3 categories. So first of all, um, uh, certification and approval. So our regulators, universally in the US and Europe and everywhere else, have determined that AI ML technologies are new and novel. And this means that applicants can't use existing guidance as a method of compliance. So this is like why the easy button on the left that I showed there is not true. Yeah, maybe you can see a way to do this for low criticality systems and satisfy the existing certification objectives, but the regulators are going to say no. They just are, because they will not accept current processes as a means of compliance. So it's, you know, the simple solution is ruled out right away. And that's why I'm a part of this committee that's working with the cert authorities trying to develop new guidance to figure out, well, what should we be doing if our current guidance isn't adequate. And that kind of takes us to the second level, second challenge, which is our assurance process. So this, I'm showing here in this figure on the right here. This is our kind of a very high level view of our current processes. This is the system development process where you it's largely governed by this document called ARP 4754, where you define the aircraft functions, the system architecture, and allocate system requirements to items, implement the system, and do a safety analysis. And then you take these items that have system requirements allocated to them, and you refine those and create high-level requirements and low-level requirements for the software architecture, implement all those things. Finally, you end up with source code and deployable code. But the problem there is, I have a copy of it. The way we get now from system requirements, refining, going through the design process, creating algorithms down to a low, what would be a low level requirement that you can implement a source code, does not work. That's when we are using a machine learning process, because instead of doing this refinement process, we go from our requirements to creating data sets for training and testing. It goes into a training algorithm and compute all the parameters that and weights and biases and activation functions that go into a machine learning model, and turn that into an inference model. And then finally, you have some low-level design that you could implement in software or in hardware. So there's this gap, right? The system process is mostly unchanged, and the implementation processes, once you get to a low-level design, are pretty much unchanged. But there's all kinds of activities that don't work anymore: traceability, coverage testing requirements, and things like that take us from system requirements down to these low-level requirements. So that's where our assurance process is heading down. Okay, and the third area is what called before the unknown unknowns, right? Which is to say, when you encounter new inputs in practice that you didn't test on, you didn't necessarily train on, but they're still part of your operational design domain, the input space that you have there to work in, you can have unintended effects. And so, I always like this picture of the guys on horses at the Whataburger drive-thru. Tesla doesn't know what that is, because it was not trained on guys on horses in the Whataburger drive-thru. Yes, something can happen. Lots of other fun examples, right? Here's the traffic lights that are on a truck. The traffic lights aren't supposed to move. They're supposed to be stationary, but there they are. They're moving. And what do I do with that? Maybe you've seen this one. I don't have the sound on, but this is the guy that made a Wile E. Coyote wall for his Tesla to see if his Tesla will drive through it. or not. And step ahead. And see, of course, that it does, because that's what has that LiDAR, like the road. All right. So those are fun. This one is not fun. This is from a recent Bloomberg article talking about an incident in Arizona a couple of years ago. If you find this article super interesting, there's lots of scary videos. But this is driving into glare, and everybody's done that. You can kind of see a little bit here around the bend. There's cars and trucks and things that are slowing down and stopping. And unfortunately, there was also a person outside of their car, and that big dent there is not from crashing into another car, but that's the person that got that. So this is all the kinds of unintended behaviors that we want to be able to detect and prevent for our aviation applications, because that. Okay, and I've showed versions of this in, I think probably the last time I was at NFM. But another main message for you is that there is no one-size-fits-all solution. And one way to try to break this down is to think about our applications in terms of complexity versus criticality. And this is sort of a log scale of, number of parameters in the system, right? So for things that are lower criticality, which if you're familiar with the deal in 78 design assurance levels, we talked about DAL A, B, C, D. A is most critical, B is least critical. Things that are low, DAL B or C, maybe up to and including vision systems, the fatigue monitoring thing that I mentioned, the cabin things, and simpler. A lot of the designs that we're doing, not for autonomy or perception, but just to compress the computing resources required, like that runway overrun detection or the optimal altitude system that I mentioned, are fairly small. All of these things we can deal with today using the kinds of guidance that's evolving, using the technologies we have, verifying through statistical methods, the performance patterns and confidence levels are. These are not going to be too challenging. People are putting these kind of things through certification right now, starting to be approved. The next things where we're going to start to be interested in some of the formal methods technologies that we'll talk about are these higher criticality systems, some C, but also DAL B and DAL A, which includes things like there's a fuel system, pressure-based fuel system that we're working on that uses neural networks. These will be higher criticality. And in order to get there, the statistical methods aren't going to get us there. We're going to have to use things like the formal methods tools for analyzing neural networks or runtime assurance architectures that people have been working on, including us, for a long time, which is also another opportunity for applying formal methods. But this, we have bounds right now on the on scalability. Lots of research to improve that. But what we're not doing yet is higher criticality vision-based assurance. So anybody that's working on the vision systems, they've architected the system so that it actually is just providing some recommendation to a pilot. So it probably is over here. But these things like a fully autonomous, I got to trust it, vision system or vision-based collision avoidance system, these are still kind of beyond reach. Or, people are actively working. Other things that we're not doing yet from a assurance and regulatory perspective, reinforcement learning, all this stuff is supervised learning. Interesting problems associated with reinforcement learning. Anything that would look like online learning or adaptation, these are things that are all trained, at home in the factory, and we deploy the inference system that doesn't change on board the aircraft. And any of this stuff, the generative AI, LLM stuff, which right now is unfortunately just sucking all the oxygen out of the room in terms of people's attention and research and things like that. So there's lots of stuff down here that is still not solved. These things, I don't know. There's going to be some interesting applications, and we'll put those together. Okay, so let me spend a little bit of time talking about machine learning safety and airworthiness. And this is just going to be ripping through a bunch of documents and definitions and things to kind of set, kind of provide a framework for how we should think about safety concerns for machine learning applications. So for aviation, all this starts with the regulations on airworthiness, CFR 14 CFR Part 25. It's for transport category airplanes, what you wrote on to get here, you flew. And the main kind of, you boil this down, if you look at this section 1309, it talks about our systems have to perform their intended functions under any foreseeable operating condition. And that means the airplane systems and components separately and together have to be designed so that the occurrence of any failure condition that would prevent continued safe flight is extremely improbable. So those are the kind of words that it uses, extremely improbable. What does that mean? And there's also where you get the idea of a single failure can't and that has to be extremely improbable, something that result in lots of safety for the airplane. So this is further interpreted by this FAA advisory circular, which describes the means of compliance with the airworthiness regulations. And it defines catastrophic. What's a catastrophic failure? It's a failure condition that would result in multiple fatalities, which generally means you lost the airplane. Here it gives you some idea for what extremely improbable has to mean. And that's where this 10 to the minus 9th number that everybody talks about comes from, right? So that's more or less connected to it. We want that kind of a failure condition should not be anticipated to occur during the total operational life of all airplanes of a given type. So if you make some assumptions about how many airplanes there may be and how, what the time of service might be, that gets you to this failure rate of 10 to the minus 9, probably 10 to the minus 9 per flight hour. Okay, so that number is a failure rate, failure per flight hour. All right, so this is really, but it's just trying to provide some intuition to engineering judgment for acceptable events. And then further, this is, you actually go to do this. There are industry documents like ARP, SAE recommended practice 3754, that starts to describe what these processes are. Those are the boxes that I had in that slide that talked about the system design, architecture, allocation, setting the valve levels for components, right? And this defines things like aircraft functions and an error. So an error is a mistake in the requirements, design, or implementation, right? So that's like a design issue, error. And then failure is something that breaks a part can no longer perform its function. So errors can cause failures. And a failure condition, it can be caused by one or more failures or errors. Right? So it's encompassing both design errors, things that happen as we're designing the system, and material failures, things that, whether it's a bit flip because of the zooming from space, or a mechanical piece of equipment wears out, or something like that. Okay, and from all that, this defines the DAL A, B, C, D, E, which map to hazards being catastrophic or hazardous or major. But this is all still what you have to see is this, we want to try to put these precise numbers on it, but the way this is all described is really pretty qualitative, right? In terms of setting a level of rigor depending on qualitatively what the consequence of the failure is when it's required likelihood. So further, I mean, this is just flashing back to that assurance process picture that I showed before. 4754 talks about the, how you assign the DAO levels in order to minimize the potential for errors. So it's really, there's nothing magical about the DAO assignment that we have for these different levels. It just sets a higher level of rigor for things that have to be less probable because their consequence is worse. Okay, and that in order to have some rationale for why we think we have made catastrophic failure conditions extremely improbable. Okay, qualitative probability involved being probabilities. All right, so getting in the Wayback Machine, since we're at NFM and near Langley, this paper back from whenever it was, 93. Butler Finelli paper talks about this is one of the early papers advocating for why we really need to use things like formal methods, because software doesn't fail, right? Like hardware systems do, but we can expose failures through evaluating different, we can expose errors, design errors, through the input conditions. You have to find the input conditions that might expose errors in the design. And failure rate would only be relate to how probably, what the likelihood of these input conditions are. But because of the numbers that we're talking about for ultra reliable systems, these 10 to the minus 9 failure rates to generate input conditions that might give you some confidence that you have achieve that level of reliability, it would, the amount of testing required would be infeasibly long, right? And so you got to do something. You have to analyze the system using formal methods and architectural methods to reduce the level of reliability that you need for any individual component, because you're so what about neural networks? Because of their complexity and the size of the data sets that we're talking about, we typically characterize their performance probabilistically. The neural networks are deterministic. I cannot tell you how many times I've been in meetings and people talk about, machine learning is hard because it's non-deterministic, and it's not. We just characterize it using probabilities because that's all we can do. That's what comes out of the training process. But put the same, put the kinds of neural networks that we're talking about, the systems that we're talking about, they're not, it's not a genetic algorithm or anything like that where you have random seeds. Put the same input in, you're going to get the same output. Totally deterministic, right? The statistical performance measures should not be viewed as development errors or failure rates. They're just part of the requirements. So when we say that this particular trained component, it can compute this, go back to the example of the optimal altitude. We'll tell you what the optimal altitude to fly at is within, plus or minus 100 feet with a confidence of 98%. Or you have a confusion matrix that comes out of an object detection system. That's just a requirement. That doesn't, if the thing is out of spec for some small number of samples, it didn't fail, it wasn't poorly designed. That's just part of the requirements. So our problem in dealing with these systems is we don't usually think about our requirements being probabilistic. Usually it's this shall happen, this shall not happen, and go write some deterministic software that does that, test it, show that it does or does not happen. We don't characterize things typically probabilistically. That's part of the problem. And people see this, these numbers like 10 to the minus 5, 10 to the minus 7, 10 to the minus 9, and think, oh, that's a detection probability for this neural network. It's not. They're not the same thing. One's a failure rate, and one is a probabilistic requirement. But what it means is that even if we could develop a neural network that produced an accurate an inaccurate output with, this some very low probability of 10 to the minus 9, we couldn't test it empirically. We would still, just like in the Butler-Finelli paper, we would need some other method to rely on for high integrity systems, right? So just summarizing the same thing, when a neural network produces an incorrect or out of tolerance output, what is it? Is it a design error? It could be. It could be that it generalizes poorly, or it's not robust, or is a response to an out of distribution input or some other unintended behavior. Or it could be that this is just part of the expected behavior given the limitations of the data and the training process. And this is, the tolerance and the confidence level that this thing has been trained to meet, which means that in some small percentage of the time, you're going to have out of spec outputs, but it's still meeting its requirement. It's really hard to know for any individual sample what it's telling you, right? But we still have to figure out what to do for safety critical systems, how to handle this. Okay, so just like for a traditional system, we can use architectural mitigations, fault-tolerant design practices, redundancy, dissimilarity, using higher DAL components to monitor low DAL components, things like runtime assurance architectures, they're, specified by the ASTM F3269 specs, simplex architectures. Maybe having dissimilar machine learning component implementations, ensemble learning type of approaches. That's reasonable. But we have to talk about what constitutes dissimilarity and independence. We have to have completely separate data sets, probably, trained separately and implemented separately. There's also systems that look at replication in time over input sequences, right? The fact that most of our computations happen again and again and again over sequences like video frames, and we can use things like output filtering to suppress transients or detect and drop erroneous or unsafe inputs or outputs. But then you have to look at the temporal independent issues between the inputs. We'll have some rationale for being, are these things samples independent after some amount of time. Okay, so where does that leave us in terms of safety approaches that we want to pursue? We can embrace the probabilistic requirements, right, and generate large amounts of verification data that are sufficient to satisfy the statistical levels of confidence that we need. And that's kind of what we did for the recommended proof level application. And in this case, we can do that because this thing, its inputs are just numbers, right? And we can use synthetic data there. Altitude doesn't have to be measured by, an instrument on an aircraft to fly. It's just a number. So I can generate as much training data for this system as I want. It can use redundancy to improve the probabilistic performance. That's what this runway overrun system does. It looks at samples over time and has sort of a moving window and has to exceed some threshold recommendation before alarm say, hey, you don't runway. We can reject the probabilistic requirements and say, no, this is a deterministic system. I want to reason about it deterministically. I'm going to use full method tools to assess the robustness by guaranteed bounds on the output of all the input space. And I'm probably going to need to do this for DAL-C higher. Or I can bound the behavior of probabilistic requirements using runtime assurance architectures to monitor inputs or outputs or both. And this is what we did in the DARPA assured autonomy example. So that's safety. So now what are we going to do about it? How have we used formal methods for sign assurance? Okay, so the real benefit here, or the problem we're trying to fix, is if you think about, here's some target function that we want to train our neural network to implement. Here's the X's or some data that we sampled, and here's the system that we trained. And there might be places in between our data points where the trained function doesn't agree with the target function, but we don't know because we didn't happen to sample there. All right. So this is great application for analytic tools that can mathematically assess everything that's happening comprehensively over the whole input space to detect these kind of violation functional requirements or accuracy for the tolerance specification. All right. Current tools, and there are lots of them, are typically based on some combinations of SAT or SMT solvers, MILP, abstract interpretation. Most, but not all, rely on you using piecewise linear activation functions like ReLUs. And they are limited by scale, but this is the number of neural network parameters. But if you ask, we could get up to millions of parameters, which gets you starting into the realm of vision systems, especially for robustness analysis. So active area, BNN comp is a competition that tries to compare and encourage the improvement of these tools. These are some of the ones that we have played with in the last couple of years. So one of the things that we've been really trying to turn into a process that we can deploy in our business units that want to use these is this formal methods robustness analysis. And that'll be presented in this paper next month on formal methods for generalization capability. But the idea is, if this is on your left, the input space, and we're talking about systems that you can characterize. These are these kind of physics-based systems, simpler systems, not vision-based systems, right? Where we have, some, 10, 20 inputs, right, that we can characterize very well. The input space of the system. Here are the sensor inputs that are coming into this thing. They have max and min values. We know what they're going to be. We know what their ranges, their resolution are. We can define the input space, right? So the idea is, if we pick any subregion in that input space and use our formal methods tool to determine, well, what are all the possible outputs that this thing can produce, and define a range of that, right? This is what that our analysis tool tells us, the max and min of this blob of the input space and put it project to in the output space, and compare that to our specification. Then we can determine whether we are within the same bounds. And the implicit assumption here is that this input space, or this target space, is well behaved, right? That the target space doesn't have some weird bump in it, like I showed on the previous slide. It's more or less continuous. I would specify this and interpolate in between any of the known points. That should sort of bound what my desired behavior is. I did have some target behavior that, didn't lie within the bounds of the set, then I need to specify. So it's a reasonable. Is that me or you? Where? It goes. All right. All right. Okay. Now we're sharing. Okay. Okay.
How do you determine the subregion? Is it like with another approximation?
I will show you. Yeah, so in this paper, we're using abstract interpretation tool to do this protection. Well, so you can there's different ways you can set this up to both find bugs and do a proof. So the way, we applied this to the recommended cruise level. But because it's a well-behaved input space, we just grid up the whole thing, right, and divide it into these hypercubes. And this analysis that says, hey, what is this little one of these small hypercubes? What does it project to in the output space? That runs pretty quickly, and so we just run that over the entire input space to do the proof in that direction and see if we have bugs or not, right? So that looks like this. Take the input space, define it, grid it up, compute the outputs. What's the max and min for any of those corners, the extremes of the hypercube. So any point, and this is our assumption, right? Any point inside that hypercube will lie within that bound, and that's a reasonable assumption for the kind of systems that we're talking about. But it's an assumption. If it wasn't, then you would need smaller hypercube. Okay. And so we can put some tolerance on that as to what we're going to accept. We run the analysis, project that for each of these hypercubes, lies within our max min bounds. Great, that hypercube is great. Go on to the next one. If it's not, we can sharpen our pencils and have a finer partition, or it might mean there actually is a problem that we need to go back to the training process and fix. So that's kind of what this process looks like. And this is, it's all nicely automated and runs quickly, and it's something that we can actually use now. Okay, did that answer your question? Okay. So I mentioned this DARPA Assured Autonomy project from a couple of years ago. And one of the cool things that we did with Boeing on that project was a bunch of flight tests of a runtime assurance demo. So Boeing put together a neural network for doing collision avoidance to maintain stay well clear separation between aircraft. And this is following the detect and avoid rules, which is, kind of the digital version of see and avoid. So it's not a TCAS, like don't scrape the paint on the airplanes, but it's more, stay thousands of feet away, avoid the other aircraft, and then go back to your original flight plan. Don't spill the beams, kind of avoidance. So that's what, so Boeing designed a neural network using, in this case, reinforcement learning to generate these flight plans. And Collins put together a runtime architecture to monitor that and switch to a trusted backup flight plan if we determined that the neural network was doing something unsafe. So the idea is this will allow the neural network to generate optimized flight plans for fuel, acceleration, et cetera, while the runtime assurance architecture guarantees safety. So when we flew this in the flight area, you can kind of see this point where all these traces cross. We had two airplanes fly at each other over this point. Of course, they're altitude separated, real collision. But that's kind of the trace of what we did on one of these sorties. So this is what the architecture looks like. Here's the neural network that Boeing has. There's also this backup planner that uses just geometric methods, and it can be verified using traditional means. And we added our monitors here to project where the own ship and the intruder aircraft are going to be and do a stay well clear assessment. And then a bunch of logic under different conditions to say, hey, what should you do? Which plan should you trust depending on what they're doing? And that was interesting because that was auto-generated by Kestrel and verified, and the logic part of it. So that's kind of interesting. So in the end, we're trying to decide between here's the neural network flight plan, and here's the backup flight plan. Which one should be followed? And so we ran all kinds of different cases where there's nominal conditions with various encounter geometries, head on or right angle or so on. We had a weather cell that was moving that got thrown into the mix that we also had to avoid. Here's one where we had an intentionally defective neural network to kind of make sure that the runtime assurance system would pick that up and avoid it. And here's one where we did some replanning to extend the assessment horizon. So if you go here, there's a cool Boeing video that talks about this, shows a bunch of these things in action that the airplane's flying. So you can find it on LinkedIn. It's also linked from our wingworks.com website. So one of the things we did here is we built an AADL system architecture model for this runtime assurance architecture, and we used our assumed guarantee reasoning environment, agree tool that we've been developing for a number of years to model this and prove that that the system does does the right thing and always gives you a safe flight plan. And it's not an incredibly difficult proof, but it's it's kind of nice to go through the exercise and identify what each of these components are doing and what their assumptions and guarantees are and how they work together, right? So the logic that you're trying to capture here is that LEC here is learning enabled component, the neural network, and BAF is the baseline avoidance function, the backup system, right? So if the LEC is safe, choose that. If the BAF is safe, choose that. Otherwise, arbitrarily choose the one that's least unsafe. And there's definitions from what you get out of the monitor to choose what those are. Right? And then you activate the switching logic to choose what it is. So this thing is safe only if you assume or separately prove that this BAF always produces a safe platform. So it's kind of what you expect. And then another thing we did, just because we could in this from the AADL model, is to annotate it and produce an assurance argument that comes out of that. This is why we believe that the system will always have a safe flight plan available, and that relies on the architecture, which relies on that architecture being correct, which is there's a branch here for our agree verification of that, and if the logic is correct, then that has a branch for the formal synthesis of the logic. And its proof, and that the backup system is safe. So that's kind of a nice thing to be able to generate that. But one other thing we did with this system, I mentioned that it was trained using reinforcement learning. So we took this neural network and we wanted to analyze that using one of the formal methods tools. In this case, we used the America, one of the Clark Barrett and Guy Katz and company have been working on for many years. And so the idea is to show that the flight plan that's produced satisfies the remainder of their separation. So our approach is to show the neural network doesn't cause the aircraft to transition from a safe condition to an unsafe condition. From one step where it's outside of the minimum separation distance to the next step is less than the minimum separation distance. That's what we're looking for. And wow, we found all kinds of places where that was not true. So we set up a bunch of candidate scenarios looking at different approach geometries. So this one, they're parallel, and you're kind of approaching from behind, approaching each other parallel at angles or head on. And we were able to find counterexamples for 5 out of 6 of these scenarios, which is not surprising because because of how reinforcement learning works. You just set up a bunch of initial conditions and you're basically running simulations and putting a cost on how that plays out and whether you end up violating the condition or not. And so it really is not covering the whole input space especially well. So it's not surprising to find things like this. So the question is now, what do you do with that? This is good fodder to throw back into the training process, right? So you can imagine other lead does the formal analysis, finds these counterexamples, throws them back into the training space to try to correct. But it's one of the reasons why currently regulatory authorities are not considering the synthetic training. That's still on its feet. Some other examples of where we've applied formal methods for property verification rather than robustness analysis. We did this also on this the RGL system, the fuel system I mentioned, the runway system, and then there's also this avoidance rerouter, which is the planning Collins planning system. And so in this DASC paper from last year, we just kind of did a survey of all the different results and what we found from that. Another really pretty in-depth study on formal methods applied to machine learning is this formula paper, and this was done in collaboration with EASA, the European authorities. And here we had a case study that was based on this remaining useful life system. So this is actually a pretty big model. It's a convolutional neural network with 1,600 inputs. It's basically taking processed vibration data from bearings, mechanical systems, and you're looking for how close are they getting to failure. So it's, it's got almost 100,000 parameters in that. So it's a pretty nice detailed use case to look at. Okay, finally, let me just give a few thoughts about large language models in aviation. What are we doing? What are we thinking? So I think there's definitely a lot of irrational exuberance in this area. If you're familiar with the hype curve, we're definitely go up in this area. Lots of hype, lots of people trying to figure out how can we use these things? What magical properties? We're going to move into the utopia of maximum productivity and new designs and all kinds of things that generative AI is going to do for us. But can we trust them? This paper is a paper that came out last year. You should read it. Pretty good. ChatGPT, yes. But this is, there's a technical definition that goes along with this. And it really means producing answers without regard for whether they are true or not. And that is simply the case. These systems are designed to produce things that plausibly could have been produced by a person. Basically completing, you provide a bunch of text input tokens, whatever it corresponds to, and it's basically using transformers to produce a logical completion that looks like other things that people have said. And might be true, might not be true. A lot of times it is, a lot of times it's really interesting. But from an assurance standpoint, this wasn't designed to produce truth, and that's a problem. One of our friends at Langley has recently published this report on using, can you use large language models to produce or assess assurance arguments? Results were not good. You're probably not surprised to hear. And here's another recent paper, just like in the middle of reading, that's looking at trying to look at these intermediate token traces that come out of the step-by-step type of reasoning that people use with large language models, and trying to look at can we look at this as a way of understanding the reasoning or thinking that the large language model is doing. And this paper says no, it doesn't really map to anything that we would think of as reason. So there's a lot of problems here, and it's also because of Brandolini's law that it's much harder to refute these things than to make claims. We in the trustworthy systems field kind of have our work cut out for us this week. Try to stand back and say, no, not yet, not for safety critical systems. Here's another fun cartoon that this fellow Robert Houston put together about the vibe testing and vibe coding. This is us, right? We have to stand up with the shield of science and math to fight off some of these claims. All right. So at minimum, we have to proceed with caution here. And as we go and embrace use of large language models in our engineering processes, there is a real risk that will cause us to lose skills in our engineering workforce. We begin to trust these systems way more than you should, just because they look good. They look like they're producing good results. And the automation is great. And man, this seems really, really powerful. But humans are really bad at being put in that role. And that's something we have to watch out for. And we've been warned about this in the past by our friend Dr. Dykstra. You should read this couple-page spree that he wrote about foolishness in natural language programming, or that. but that's not to say there's not good use cases, and formal methods are really one of the great matches here, right? Where we can use AI to improve our proof processes. And we can do this because we're working in a world where we have a way of determining what things are true or not. So college has done some work with University of Kansas, generating candidate lemmas and proof strategies in the peer improving environment. We've got an Agree Copilot for understanding counterexamples, and we're doing a season test with for this. Turn that around, how do you use formal methods for AI? Amazon is putting a lot of effort into this. So a lot of our formal methods friends who are now at AWS, there's a lot of what they're doing is deploying systems where you can look at the outputs of LLMs if you're in a domain that has rules that can be analyzed and checked to be able to determine whether the outputs that you're getting actually conform to the rules of that domain. And so this is kind of when you can do this, what you're doing is generate code, and test cases. There's something else where you have a way of verifying the output, especially using formal methods. That's a great match, right? So this is an actually really interesting use case that on this slide. Okay, final thought. This is if you ever listen to this Cautionary Tales podcast, it's pretty cool. Talks about a lot of historical engineering examples. This particular one about the Air France 447 crash from 2009 really takes a new spin on it, related specifically to the loss of skill due to trusting computing systems. And this didn't have anything to do with AI, but the principles are the same. He brings into a lot of these studies on what happens when people are given AI tools for generating design and things like that. Excellent. Worth a listen. Okay, here's just links to some of the things that I talked about. Thanks to the Collins Trusted Methods team. These are folks that contributed to all the stuff that I just talked about here. And in summary, we're going to be using AI and ML technologies to meet the demand for increasingly autonomous aircraft, but there's lots of changes that we talked about related to assurance processes, certification, and performance, the unknown unknowns. Full methods will be a key to the use of AI ML when safety critical, these higher criticality applications on the right. And LLMs proceed with caution. So full methods may be the magic that help us do that. That's it. Thanks.
Any question? Thank you, Darren, for your wonderful presentation. And we have a few minutes for questions. Anyone?
Yeah,
Thank you, Darren. Very nice talk. At the beginning, when you identified like three issues or with the use of ML in the processes, the second was
assurance processes.
Assurance processes, where you said that like this translation from a high-level requirement to low-level requirement was a little bit skipped or hard to argue.
Right.
But maybe it's not politically correct. But to me, we have the same issue with the basic control. Because when we ask a computer scientist to implement a PID controller, the values, like the weights, if you want, of the PIDs, come from like a land you don't know. That's like from above.
As a software engineer, that's true.
At the software
level.
But
in control theory, in control world, you have theoretical foundations for how you came up with those.
I agree, but since here we are, all the argument was at the level of software. At the level of software, you don't have ways to argue that those values are.
But you don't relevant. You need to have some way of knowing that whether those parameters are correct or not.
Yeah, but so let me just finish. So to me, maybe the answer is to say that all this field of AI is not a software thing. It has to be. I don't know if it's at the proper solution, but maybe people developing AI should develop their own like mathematical theories to argue about the good
Yeah.
features of their system. And then we can use the same thing as we do for control. Or if you want to address their verification at the level of software, maybe we should do the same for control.
Perhaps, but this is essentially what we're doing. If you look at the so work on this has been going on for probably 5 years to come up with, how are we going to think about this from an assurance process standpoint. And the EASA has published several of these concept papers. And they're advocating, a W2V kind of approach, and there's pros and cons to that. But the idea fundamentally is this: what they're calling the first V is the process that we need to have to add that kind of assurance for machine learning model training creation. Create the model, verify the model. What do those processes look like? They're going to be different from what we use for software. But then once we get to that verified model, hand that over to the software people, just go and implement it. It's just a math function, right? Show me that you implemented this math function correctly. The first V has to argue for why that math function is correct. And that's what we do for control here. And so defining what that first V is a lot of what's going on in our work with the regulators now and this G34 SAE committee. Yes.
I have a question. It's more of a comment. I have a control theory background, by the way. So in control, yeah, in control theory, we have robustness, margins, bandwidth, all kinds of specifications.
Yeah.
So when I argue with my machine learning friends who are like, it's a religious war, literally.
Yeah.
But the question I get from them is, I saw your the example that you provided, where I think she asked the question. You identify like a sub-hyper region.
The robustness
Exactly.
analysis. Yeah.
And then you're also specifying the expected values, like outputs.
The outputs of the neural.
Exactly. So if it's a regression problem, and again, I also work in finance. So when you do that, the argument that you get from machine learning people is, that's why statistical inference from these guys have spent decades developing sampling, distributions. So we are doing it today. So how do you actually, what's the crux of the model that tells me? Because in deep neural net today, they don't even know why it works. They don't look for features, right? They're trying to use all kinds of advanced physics. So my question is, how do I give an assurance to someone who's deep into machine learning, using it, and saying, I don't see it that your guarantee is really foolproof, especially for out of sample.
Right.
So that's what they're doing. They're bagging, boosting, resampling. That's what they do to make sure that the training data has been coverage for the entire distribution, right?
Yeah, there's a real art to what those folks are doing, and they have been doing it for a long time and producing a lot of good tools and things. And what we're trying to do here, I think, is kind of decouple the development process from the verification process and say, well, okay, you used all kinds of cool algorithms and heuristics to come up with these parameters, but we still have to have the way of, having some confidence that there's not unintended behavior in between the points that we sample. That's really all that we're trying. That's the main point, the main issue, the main problem. And so if we can use our formal methods tools to allow us to look at these in-between spaces and bound them, that, a lot, it may be fine, right? But we have to have some evidence, some reason for knowing that's fine. There may be other ways of doing it, but this kind of mathematical analysis on what's happening, I don't know how you trained it. I don't know why those weights are what they are, but I can analyze the inference system. This is what it does. We can analyze that and we can reason about what happens.
Fair enough. And one just quick question. So you said abstract interpretation, that's one level. Are you using model checking? Will you keep talking about property verification?
Yeah. I showed just a few tools there, and we've used both. Like a lot of abstract interpretation is a great way to do this forward projection, but we've also used Marabou, which is really more of a model checking style to deal with the transitions and the piecewise linear activation functions and all those different combinations using the set solver part of it and MILP to deal with the math.
No, thank you. Excellent talk. And by the way, I read your entire DO 333 paper report from 2014.
Oh, wow. Okay. Thank you.
Any other questions? Yeah, okay. All right.
Thank you for the great talk. Had a quick question on you had the example of having a target function and then trying to learn that function in
Yeah.
a neural network. What type of example, I guess, would there be a target function? If you know the function, why not commit the function as opposed to try to create a neural network?
Right, because it might be really complex to implement. So one example of that is this fuel system. Its inputs are a bunch of pressure sensors. So normally you have capacitive probes in fuel tanks that measure the height of the fuel. Pressure sensors can do that without having like electrical connections into the fuel tank, so it's safer. But you have to somehow say, okay, I got these pressure measurements. What fuel level does that correspond to? So if you think about it, and fuel tanks are really weird shapes, so they have to fit in quickly. And there might be different angles and all of that.
Okay, so there could be some uncertainty in the
Right.
modeling of.
Well, it's not that there's uncertainty, but if from first principles, it's very hard to say, I got these pressure readings, how much fuel is in the tank. It's very easy to say from simulation, oh, here's what the geometry of my tank is, here's how much gas is in the tank, here's what the pressure sensors will be. So I can generate crap loads of data, as much as I want, or arbitrarily much data, to learn that very complex function that would have been extremely complex, if not impossible, to calculate in first principles. Thank you.
So we're at time. So if you have other question, you can catch up with Darren during coffee break or later today. So let's thank our keynote speaker again.
Thanks, everybody.
And we restart in 20 minutes for the first session. Thank you.
Okay, so we are going to start the next session, and it's the session on Turing proving. So after the nice presentation by Darren on this morning, we are going to continue with the topic of neural network verification. And our next speaker is Sigi Atala. He's going to be presenting virtually. And the title of his presentation is Process Algebraic Semantics for Verifying Intelligent Robotics Control Software. So, Sig, please go ahead.
Okay. Hello. I trust all of the. I trust everyone can see my screen. That's all working for sure. Right. So, thank you very much for that introduction. And yes, no, very sorry I couldn't. I can't be here for this conference. Everyone enjoys Williamsburg. It looks very nice. But yeah, so. I'm a researcher. I'm a research associate working in the RoboStar Center of Excellence for Robotics, as I can show on the right here. A very large research center focusing on how we can develop software engineering for robotic systems. And I'm also working in the RoboSapiens EU project for safe adaptation, unprecedented situations, for safe unprecedented situations. So first, I'm just going to go over a brief outline of what I'm going to talk about today. So first, I'm going to go over a little bit of background. Then I'm going to go over our AI components in RoboChart, which RoboChart is a domain-specific language for modeling robotic control software, for modeling the control software that we use in robotics. And go over our tool chain, how we can model and verify these components. Then I'm going to go over how our approach for how we can verify these software models when they have AI components in them. Then we'll go to brief conclusions. So first, yes, indeed. After following on from after this is Darren's presentation. So as we know, verifying systems involving AI controllers is a very big topic, and I'll give a lot of answers to it. It's a very in development area, but there are three key properties that we can talk about when we talk about systems involving AI. Is that the system overall should be interpretable. We should be able to know how the AI module has come up with a decision. We should be able to explain those decisions that the AI component does produce, and also they should be precise. When we're using AI controllers for regression, there is an inherent numerical instability when we're using them. So we need them to be, the systems involving them to be precise regarding this imprecision. So there are two main ways in the literature right now that people are modeling and verifying systems involving AI controllers. The first method is by using hybrid automata, where you model the robotic platform itself, as well as the software as various components in a hybrid automata. We verify properties about that. This is more for the verification of robots involving AI, not so much for the design of them. So then there's a few authors that are proposing approaches that are based on the unified modeling language, where we can consider AI components and modules as separate controllers. So the word ANN controller, AI controller, is being used a little bit in the literature so far. So let's just put it in context so our work is modeling and verifying ANN components of RoboChart. So specifically, right, we see this as the beginning of this approach, which is so we're modeling feed forward a fully connected neural network components and trained neural networks for control right now, and this is what we're reporting on right now. So what we've done for this, one of our key contributions is first, we have defined a profile of conformance. We define a conformance relation, which is a modified refinement to take into account numerical imprecision. And we have so we can deal with some of the precision aspects of systems involving AI controllers, and also we have generated verification conditions for this conformance relation for conformance systems. We've generated a strategy for generating verification such that they can be discharged by ANN specific verification tools such as Maru, was actually mentioned by Darren as well. So first I'm going to go over what RoboChart is. I mentioned it's a domain-specific language for modeling and verifying robotic applications, specifically control software used in robotics. So it supports verification when we consider timed, probabilistic, and reactive properties through a variety of methods. So its semantics is based on Circus, which is a combination of Z for data-oriented aspects of system, data-oriented specifications, CSP for reactive and process-oriented systems, and refinement, because it has some built notions of, it's combined with a refinement calculus as well. So RoboChart has a denotational semantics in Circus. It's one of the key features of RoboStar notations is the denotational supported compositional verification approach. So it's supported by RoboTool, which is a set of Eclipse plugins available at the link below that provides automation of our approach. So it provides model checking using FDR4 phase version refinements for CSP and Prism for probabilistic properties. Also, we currently in development is an approach to enable theorem proving in RoboTool, which I'm going to talk about a bit later, but theorem proving in the proof assistant Isabel to enable automated theorem proving using RoboChart models. So now I'm going to go over an example RoboChart model and an example little robot. So for context, we have this two-wheeled balancer Segway robot that is designed simply to balance and to stay upright. It does this through 3 PID controllers. Now, on the left here is the RoboChart model of the control software. So this segue and the overall block we refer to as a module in RoboChart that describes the model of the entire software. Then we have the main controller, which is defined here by the segue controller that defines the primary behavior and defines the 3 PIDs. We're going to talk about in a minute. Then also very key to a RoboChart module, to the method of modeling systems in RoboChart, is this idea of a robotic platform. This robotic platform captures the assumptions that we require about the robotic platform for the system, which is a model of the sensors and actuators of the actual robot that the software relies on, that the software assumes exists. And then the third aspect, as you can see here, is this neural network component. So what I've done for this example, what we're working on for this example, is we had an angle PID. We had an angle PID component that's defined by a state machine, similar to, so here the state machines of rotation and speed PID, and then we replaced that with a neural network component that we refer to as angle PID ANN. This is one of our contributions. So angle PID ANN, how we specify an ANN component inside RoboChart is through 3 internal blocks. First, the parameters defines both the hyperparameters and the train parameters of our neural network model. So we can see here the activation function, the layer structure, the weights bias, and then we have parameters for normalization as well that I will go over later. Then we have the input block that defines the inputs that the component the input that the component relies on to the input events the component relies on, represented by ordered events here shown by the 1 and 2. We have outputs for the outputs of this component. Also, we can define these parameters via a file format for larger ANNs. Of course, for smaller ANNs we can just use define in the language itself. So I'm now going to go over, given this RoboChart with ANN components, what our approach actually is. So given AI-enabled robotic software, some robotic software that involves one or many AI components, our first step is to model this inside RoboChart with ANN controllers that is enabled by RoboTool. Then after we've done this, we have two semantics, right? The first semantics is this is the circuit semantics that we generate via a model-to-model transformation, which we can then enable theorem proving with. And the other one, we have a translation to CSPM for verification SVR4. Right now, this is quite limited, just only about structural properties, but could be something to explore within the future. So going down to the circus meta model, we can enable a view in CZT circus just for viewing the semantics in a nicer way. Then after we have these semantics inside RoboTool, this is a set of plugins I was mentioning, we then define a model to text translation, which takes our circus semantics and encodes them inside is a circus, which is what starts to enable the theorem proving with these models. First, with is a circus itself, we can describe some we can describe some multi-phase verification using verification rules, but then we translate these in something called Isabelle UTP that I will go over more later. But this translation to Isabelle UTP from our circus semantics enables the integration with Marabou, as is based on fundamental relations, as based on alphabetized relations I'll go over later. So this is our entire tool chain for the verification of RoboChart models involving neural networks. So I'm now going to go into what the circus semantics for our ANN components actually looks like. So circus is you can see it as a process algebra where processes engage various events similar to CSP. So on our top level process is just one that say you have a channel in that just engages in any number of input events on this channel, a number of input events, then outputs a number of output events. As we're dealing with NS for regression right now, we're saying the real numbers input and real outputs. Then after this, our first submodule inside an ANN is the interpreter that allows input in any order and produces output in any order, increases the responsiveness of our ANN components, and has potential further development as well. So the interpreter also normalizes the inputs. All of the values that are received from the input events are then normalized and fed one at a time into our process algebraic model of a neural network. And then of course, afterwards it's denormalized such that it can engage with the rest of the system if such normalization is present. So as a process algebraic model of a neural network, we first have that the hidden layers and the output layer are another process that are in parallel with each other. Then also we have inside each of these hidden layers, we have an arbitrary number of hidden layers, which are each again a process that interacts in parallel with all other processes, with all other layers. Then inside the layers we have the parallelism of nodes too. And in each node we actually have each edge represented by another process, and it communicates on an internal channel node out and then feeds to the layer res channel that represents the communication between the layers of a neural network. So given these semantics, so we have, as mentioned, we have automated generation of these circuit semantics. Now, what do we actually do with them? So this is what I see. Yeah, absolutely. So our verification approach at the moment, considering we have ANNs for regression, our verification approach is based on this area of conformance. So when the Circus also has a denotational semantics that is based on predicative alphabetized relations. This is this Isabelle UTP that I was mentioning earlier. And the reason why, and we translate into these semantics to enable the description of real number generation verification conditions. But also when we're inside here, we can define a notion of conformance. This is one of the central contributions of our work. So first we say that a process P is conformant to Q, if and only if the approximation of Q is refined by P. Now, these two parameters are extremely important. When we talk about conformance systems, we say that we have some epsilon that shows the actual the degree of approximation. Then we have C, which is the tainted channel. So we say that all communications through this tainted channel C are approximated by epsilon, which we represent using our approx function, which takes Q and returns another process that is a more non-deterministic version of Q, that whenever it sees in its traces the communications via the channel C, then approximates them by epsilon. Then we say that this is a non-deterministic version of Q, and that is defined by P. So just to double check, the P is the implementation here, which is the other way around with normal refinement calculus. Q is a specification, and we say C is the tainted channel. Now, to give a very quick example of this implementation, normally, of course, we consider neural networks as having an output on the real numbers, as some real numbered output. But for the sake of demonstration, let's just consider the channels that communicate via natural numbers. So in our example, first we have if we say these two simple CSP processes, buffer that receives any input on some channel in, and then outputs that same output, and we have M buffer, a similar process, but that outputs that value incremented by 1. we can prove conformance between these two processes. So we can say that an M buffer conforms to buffer, where the epsilon we take as 1 and the tainted channel we take as out, where just, so the in channel is not tainted. So in our formulation, in channel would remain exactly the same, but only the out channel we modified. So as shown from above, we can demonstrate this if we have that the approximated buffer is refined by M buffer. So the definition of this is a simplified definition of the approx is the approximate buffer is equal to the standard behavior. This is the first one, non-termically composed with the same behavior, but where the out channel has been decremented by 1, again non-termically composed with another process where X has been incremented by 1. So taking the just kind of approximate the channel in kind of a ball around around epsilon, the channel communications. So we have that this is that the above is refined by AXL1 using the standard laws that refinement reduces non-determinism. So then, and we have that equals M buffer. So this notion is fairly this notion seems fairly simple, but why is it interesting and why I'm pursuing it? I want to give a brief example of why this is interesting and what we can do with this notion. So given we have the same module shown earlier, this segue, if we have segue ANN, that is the segue with the ANN component, and segue which is a segue without the ANN component, which is angle PID implemented via state machine, we can say that segue ANN is conformant to segue, given that we approximate the channels set left motor speed call and set right motor speed call. That corresponds to an operation of the robotic platform itself, and this corresponds to the top level event in our CSP semantics for the entire segue, for the entire module, that is. And we can soundly conclude this through monotonicity laws of conformance. That is, if we have that angle PIDA and then the ANN component is conformant to angle PID, then we can soundly establish through laws of monotonicity that the entire system is conformant with respect to epsilon. We can show this through, through the communication of angle PID with balance STM, balance STM engages in the motor's eye interface. So then the last thing to say is then how do we actually, the last stage of our approach is how do we actually prove this? Because of course we have this inside Isabelle, and Isabelle is able to scale to large ANN models due to the complexity of the verification problem. So we enable a translation to verify. We enable translation to dedicated ANN tools. We're specifically targeting Marabou, but these conditions it remain open to extension with a lot of other ANN tools as well. So first, we say that that for all x1 and x2, inside these specific ranges, these ranges minus 30 and 30 are from the expected inputs of the system, from normalized ranges of the system. Then we say that the denormalized value of ANN input with respect to normalized, basically this is just saying that the ANN's output, which we, as I mentioned before, with the normalization based on the interpreter, the ANN's output is within epsilon to this function S, which we say is just a monotonic function S that captures the specification in terms of the relationship between the input events and the output events for a controller. And we say that S here is, because it's a simple PD controller, it's some simple linear function. And then we say that if we have this, we must have conformance between our ANN component and our controller. Now, our strategy, yes, we can discharge this with Marabou, given that we have a low input size and we have the S is monotonic, because our strategy at the moment for generating the verification tools is based on input domain splitting, based on slicing of the input domain. So scaling to larger so scaling to larger input sizes with larger values of splits is definitely a challenge. But we have observed that in a lot of robotic control problems, especially in a lot of, say, either forward or inverse kinematics or stability problems, we can model them quite successfully with low dimensional with low input dimensional ANNs. So finally, just want to give a brief summary about what we've done and where we're going. So we're trying to enable a tool that enables automated software engineering with AI components, and this is work that was started in my PhD thesis and continued with this paper published in ICTAC. I see it as an ongoing project. And what we've got so far is we have automated modeling. We have automated modeling, validation, and editing for models of systems involving AI components. And we have this available as plugins. We have a graphical editor for this as well. We have automated circuit semantic generation, and not only defined semantics, but automated semantic generation via an Eclipse tool that implements multimodal transformations. Then we have an automated translation to Isabelle via a multi-text translation. Now, for the future, there remains a lot of interesting directions I see. So first and immediately, we want to be automating the monotonicity theories for conformance. So as I mentioned before, the monotonicity theories for conformance enables us to reason about conformance as a conformance systems that involve AI components, or a key contribution of our work. We're going to automate those and integrate those with RoboTool. We're also going to automate our translation strategy to Marabou, which is enabling an automated connection from Isabelle, specifically Isabelle with the unifying theories of programming I mentioned before, to Marabou, enabling the full automation of this tool chain. Now, the third direction is applying further applying the properties of our process algebraic semantics for neural networks further, which absolutely can include some with some considerations for say recurrent neural networks or other types of neural networks based on the process algebraic nature. And finally, this entire work as I see as steps towards enabling reliable engineering with AI components. Thank you very much for listening. Thank you very much.
Thank you.
Thank you.
Excellent. We have time for questions.
Yeah, sure.
Anyone? So let me start with one. So you have in this slide you talk about translation to different from model to model, from model to text. So you have different translation to tools. How do you know that you are translating all those things correctly, that they translate, that you preserve the semantics when you do that translation? I mean, is that, for example, when you translate to Isabelle, because in Isabelle you have a term proof, you have a proof of the translation, or this is just validation? And
yeah, actually, I'm just going to, if I can go back quickly to, okay, so getting into more some of the details of how this is done. We're based on the Epsilon framework. So Eclipse modeling framework, we're based on, we use Epsilon to implement these multimodal transformations in RoboTool. So because of this, we don't have a formal semantics for this transformation, but we have we have semantic rules, we have abstract semantic rules, we have semantic generation rules that we then try to ensure that the implementation of these multiple transformations conforms to our specification. We have a specification for these because we don't have a semantics of Epsilon, can't prove, but when we get into Isabelle, this translation, because we have the translation fully inside Isabelle, we can prove it's actually worked by with Simon Foster and Fang Yang with other people. That is the translation from that we can prove entirely as sound from first principles using Isabelle's using Isabelle's technology. And finally, just to say, translation from Isabelle UTP to Marabou. The full proof of that is still ongoing right now. It's more of a call, but the full proof of the integration, like reproducing Mary's proofs inside Isabelle, is future work for sure. But yeah, for sure. But yeah, thanks for the question. But yeah.
Okay, thank you.
Thank you. Thank you.
Yes.
All right, thanks for the talk. So I have a question about the design choice. So you are talking about the ANN controller, then you use this circus semantics to sort of describe the behavior of the controller. I'm curious about why you choose this semantics, this process algebra, and instead of others, for example. And do you think it's good enough to cover the behaviors of the controller?
For sure. So this is a very okay. So first, the process algebraic semantics, it enables us to reason about there's this new specification type, I don't know if we're, but neural activation patterns that is being more talked about, and it allows us to we want to define the specific when a neural network is accurate based on the patterns of activation, and partially our semantics can support these specifications very well, but also we can so say if there's dead nodes if there's dead nodes present in the neural network, we can use refinement calculus quite easily automatically identify these dead nodes and then go and make another model, a simplified model. And also with conformance, we can make simplified models. So for example, we're reasoning about width and depth of these systems. And that's the kind of the first reason. And the second reason is by using the notion of weakest fixed point calculus as used quite a lot in process algebraic semantics, we can capture the recurrent connections quite easily using this future work, but it allows the potential for capturing recurrent connections in a different way, recurrent connections in quite an efficient way using weak fixed point calculus. For sure, and so for other engineering constraints. But yeah, this is that's why the final future direction was applying out the nature of these semantics further to more types of, say, classification network or more types of neural network themselves. So this is definitely future work to explore that side of it further. But yeah, thank you. But yeah,
Excellent. Thank you. Let's thank the speaker, and we move to the next session. To the next topic.
Okay. Thank you.
So let's change the topic. Now we are going to talk about verification of blockchain. So our next speaker is Pranab Gopate, and he's going to talk about reusable form of verification of DAG-based consensus protocols.
Hello. Okay, so I'm Pranav Gopate from University of Sydney, and the topic is based on reusable formal verification of tag-based consensus protocols, and this is a joint work with Natalie Bertrand, Sasha Rubin, Bernard House, and Paul Phillips. Okay, just to give you a bit of context about growing interest in tag-based consensus protocol. This is a figure taken from IPv3 24 survey paper. The x-axis we have years
from 2015 onwards, and on the y-axis you have total number of tag-based consensus protocols introduced. And it shows that in the last decade or so, more than 15 new tag-based consensus protocols have been introduced. The primary reason for this is that these protocols kind of improve over classical blockchain protocols by providing higher performance, lower communication complexity, and at the same time tolerating Byzantine failures. As a result, many of the modern blockchains kind of actually adopted tag-based consensus protocols as their primary consensus mechanisms. Some of the examples include Hedera, Phantom, LS0, and 3. Given that billions of dollars are locked into various of these blockchains, manipulating consensus protocols is a natural attack vector. Attacks such as double spending attack try to kind of exploit the unsafe consensus mechanisms to spend a single unit of currency more than once. And thus, a rigorous formal verification of these consensus protocols is necessary. Okay, so there are various directions one can take towards verification. One can try performing testing, but testing often misses quantitative intelligence and the distributed asynchronous setting. Testing also misses to capture the precise Byzantine behavior that would actually jeopardize safety. One can also perform model checking, but it does not scale to real world instances, which range from hundreds to thousands of processes, whereas the state-of-art model checkers can perform model checking for let's say 10 processes. The techniques in parameterized model checking are not yet expressive enough to capture the complexities of these tag-based consensus protocols, and thus theorem proving remains like the only viable option for rigorous formal verification of these protocols. Theorem proving comes with its own cost, that is considered complex, tedious, time-consuming. And given that there are so many of these tag-based consensus protocols, verifying each one of them from scratch is infeasible. So towards this, our work kind of demonstrates that these tag-based consensus protocols are actually amenable to the practical, reusable, and compositional formal methods. We show this by verifying verifying safety of 5 tag-based consensus protocols with a reduced proof efforts of by almost 50%. So these protocols are tag writer, cordial miners, Ashgraph, eventual synchronous pulsar, and a minor variant of LF. Our approach involves identifying the right abstractions that would decompose these protocols, specifications, properties, and flows into modular components, which then can be used. Okay, so and our experience actually tells that these and many other tag-based consensus protocols share the same fundamental principles, but the variations are introduced to kind of improve the performance. Nonetheless, these variations can impact safety significantly. Okay, so for the next 10 minutes or so on this talk, I'm just going to talk about these tag-based consensus protocols, the similarities, the fundamental principles they share, and the similarities and differences between them across these 5 protocols. And in the last 10 minutes, then I'll kind of introduce our abstractions that we identify to maximize the closed field, and then talk a bit about safety flows and CLA costs. Okay. So tag-based consensus protocol solves this Byzantine atomic broadcast problem, which states that there are n processes in the network. Some of these processes can be Byzantine faulty. Each process can propose or output blocks, and blocks is just a set of transactions, or you can think of it as a network of blocks. And so one has to ensure that all correct processes eventually output the same set of blocks and in the same order, which is agreement and total order. No correct process outputs same block more than once, which is integrity. And a block proposed by a correct process is eventually output by all correct processes, which is valid. Now, in terms of safety, the most critical property of this total order, which again says that the output sequence that any two correct processes output has to be consistent. That is, one has to be the process of the other. Now, these tag-based consensus protocols actually solve this Byzantine atomic broadcast problem in just 2 phases. First is a tag construction phase, where processes communicate their blocks and build a directed cyclic graph. of the exchange block. And after this, there is an ordering phase where processes use their locally constructed tags to determine the total order of the block. And this ordering phase actually happens completely offline without any additional communication, purely based on the information that is present on the local directory. Again, now I'll go over each of these phases, give you a brief idea of what's happening there, and also talk about the variation within these phases across the 5 protocols that we mentioned. Okay, so tag construction phase, you can define this inductively. Initially, all processes have empty tags, and let's say at a given point in time, let's say we have 3 processes in the network and their tags look something like that. Now, whenever a process wants to create a new block, it creates it in the form of a vertex. And so when it creates this new vertex, for example, P3, if it wants to create a new block, it will create it in the form of this purple vertex. Now, when creating a new vertex, the process has to include 2 things. It has to reference this newly created vertex with already created vertices in the past. And so when P3, process P3 creates kind of this new vertex purple, it has to ensure that it first references this newly created vertex with the last vertex that was created, which is the blue vertex. And additionally, it can reference to some other vertices on its own local time, it's the green vertex. Now, different protocols impose different restrictions on what these other vertices can be, but I'll talk about those restrictions. Okay, the next process kind of just broadcasts this newly created vertex along with the hash values of its references to all other processes. And whenever a process receives a vertex from other process, it first checks if it has all its references in its own local DAG. If it has, it adds this newly created vertex in its own local DAG, otherwise it goes within a buffer. And wait for the references just to be added before adding this newly created vertex. Okay. And so in this example, when people receive this broadcast message, it has this reference with vertex blue and green. So it will just simply add this purple vertex, whereas T1 does not have the blue vertex. So it will first wait for the blue vertex to be added before adding the purple vertex. Okay, so that's like for that transcription. And now an immediate property that the stack transcription ensures is that if a vertex is present in the local DAG of 2 correct processes, then its causal history is absent, which is consistent causal history property. And what this means is, and by causal history, I mean the sub-tag induced by all the reachable vertices from this vertex. So in this case, the sub-tag induced by this puzzle vertex. Okay. So now variations within that construction phase primarily stems from this 2 factors. First, it's communication. That is the communication primitive that these protocols use for processes to communicate their newly created vertices. And protocols like TagWriter, Bullshark, and Aleph use reliable broadcast to communicate their vertices, whereas protocols like Codel, Minus, and Hashgraph use unreliable communication, which is like simple or plain broadcast. Okay, and why does this affect? Well, depending on what communication primitive we use, the local DAGs of processes might or might not have these codes. So the forks is a Byzantine behavior where they do not follow the tag construction procedure and create vertices which do not have, which neither of them have paths from one to the another. I'll not talk about what these forks are, but keep in mind is that whenever the protocol uses unreliable communication, these forks might be introduced. Whereas using reliable communication, one can actually avoid this Byzantine behavior. Okay. And the next variation is depends on the type of DAG that these protocols construct. So there are again 2 variations. Protocols like Hashgraph construct an unstructured DAG, whereas remaining all protocols construct a structured DAG. And this is again depends on how new vertices are created. In structured DAG construction, new vertices are created in ground, and they impose the restriction that the references of these newly created vertices in round R has to be from round R minus 1. As a result, the local DAGs of each processes look something like this in a structured format. Whereas in unstructured data, there's no such difference. So you have to arbitrary that. Okay, moving on to the next, to the ordering phase. Now, again, the objective of ordering phase is kind of processes use the local DAG and determine a total order on the vertices in the local DAG. And this has to happen without any additional communication. Okay. And a simple procedure for this is that first processes partition their local DAG into sequentially numbered frames. So here we have frame 1 and 2. And as the DAG evolves, new frames will be introduced. Then they have to agree on an anchor vertex for each frame. Now, somehow they agree on an anchor vertex. Different protocols use different protocols on how to kind of agree on these anchors, but I'll not go into those details. So for this frame 1, let's say they agree on an anchor vertex 1. For frame 2, they'll agree on anchor vertex 2. And because of asynchronous, some processes might not have anchor vertices on their own local DAG, but one has to ensure that eventually they'll have these anchor vertices. And now, since our DAG construction kind of ensures consistent causal history property, where one can actually totally order the difference in causal history of these anchors in some deterministic order. So the causal history of anchor 1 involves vertex A and B. This can be ordered in some deterministic way. And then the difference in causal history of anchor 2 and 1, which is vertex A and B, which can be ordered in some deterministic way. Okay. So that's how one ensures total order. The two properties, one is anchor agreement in the ordering phase and the consistent causal history property in the DAG construction phase. Okay. Now, the variations in ordering phase primarily are introduced by how processes agree on anchor. And then there are two broad categories in there. Protocols like tag riders, corridor miners, and Bullshot use global perfect points to agree on anchor. So just it's like kind of global perfect point based anchor agreement. Whereas Aleph and Ashraf use virtual voting based anchor agreement process. Again, I'm not going into the details of how they differ. But within these categories, there are variations, and they primarily stem from how the DAGs were structured. The cordial miners and Ashraf use unreliable communications construct their local DAG. As a result, they have hosts in their local DAG, and thus this anchor agreement protocol has to additionally consider this possibility of hosts. Similarly, Ashraf constructs and unstructured DAG, and thus it has to kind of first pre-process the unstructured DAG to a structured format before actually applying the anchor agreement protocol. Okay, so those are the examples of similarities and differences between these 5 DAG-based protocols. And as you can see, there are a lot of similarities which can be exploited to kind of use the code. So towards that, I'm just going to swap these two columns, anchor agreement and anchor system, nothing else changed. And so again, our approach is to kind of identify the right abstractness that will decompose these protocols into modular components, which we can then use. Okay, so a nice place to start would be to decompose these protocols along with aspects, along which they are actually defined. So DAG construction phase and ordering phase. And by decomposition, I mean you abstract the DAG construction procedures from your protocol specification. And what you really have is just the ordering phase specification. And then you verify the properties. And in the side, you also verify the properties of your DAG construction specification procedure. And then you kind of compose them to give an overall safety guarantee of your actual protocol. Okay. And if we go with those factors, as you can see, there is clearly a proof field happening in the DAG construction phase as the reliable structured DAG construction in the DAG writer is being reused in Bullshot and Aleph. But there is not much of a proof field happening in the ordering phase, as each protocol has like almost distinct ordering variations. And so towards actually kind of maximizing the proof use, we actually decompose these protocols along with new access. And so what we do is basically isolate the DAG processing and flow handling procedures within anchor agreement protocols and kind of abstract them from ordering phase specification and switch them to the DAG construction phase specification. Okay. And so with this, what you really get is there are only two main variations in noise and phase specifications. And so overall, you just need to kind of verify the 5 modular components, and then you can compose these components to kind of give overall safety verified specifications for the 5 chassis. And yeah, that's what we do. So we have the 5 modular components, which we call building blocks. We have 3 for diagram section and 2 for origin. And then we compose them to give safety verified specifications for the 5 chassis functions for the function. And our specification for the full protocol is actually refinement of ordering specifications that includes the diagram section specification. For example, here in the cordial minor, it is refinement of EPC ordering specification that includes that concept. And PLA Plus actually allows one to specify such kind of specifications and to kind of inherit the guarantees of this building block onto your protocol. One has to additionally do a refinement theorem. With that, you can actually imply safety of the protocol. Okay. Now, proof doing in PLA Plus. Further, so we specify and do our right safety proofs in PLA Plus, which are checked by PLA proof system. And there's no specific reason we go with PLA Plus apart from its kind of popular and distributed system community. But some of the things that it checks is that it produces a specification that is closer to the implementation. So the specification is in the form of transition system, action leader transition system. And it also can actually produce execution traces, which can help you debug while writing the code. And additionally, you can use these execution traces to actually map your specification with the implementation and check that implementation with specifications. Kind of match. And finally, it supports this interface refinement with which you can actually perform responsibility. Okay. So our safety properties are actually specified as safety invariants of our processes. And in PLA Plus, you prove safety invariance by induction. And so the hardest challenge in this style of verification is that one has to identify inductive invariance that would imply your safety invariance. And just to give you an idea about this challenge, here is how we verified safety of GPC ordering specification, which is one of the ordering building blocks. And the safety there is specified as chain consistency and chain monotony safety invariance. And to prove that, we had to identify 10 system invariants. And some of these invariants are proved inductively. So the ones that are on the leaves are actually proved. They are inductive invariants and are proved inductively independently. Whereas some of the invariants are proved assuming already proven. So a node is proved, a node invariant is proved, assuming it's proven invariant. And just to give you an idea about how proofs look like in PLA Plus, here's a proof of one of the invariants. And all the specifications and proofs are actually on the record. Okay, so to conclude, like the evaluation, so we have the 5 building blocks and their specifications, and we have some notes. And the important rules here are the number of invariants and the size of code. And the number of invariants are the number of invariants required to kind of prove the safety property. And these ranges between 6 to 18. And the size of those plans also range between a couple of hundreds to a couple of thousands, few hundreds to 1,000. Okay. And the size of these plans is from where we actually compute the reduction in proof of work. So if one had to prove all these protocols from scratch, one would require roughly around 9,000 lines of code, whereas we only write around 4,500 lines of code. So reducing the 50%. Finally, there is time that PLA proof system takes to check these proofs, and it takes roughly between a minute to 10 minutes. That's what for it. Okay. Conclusion. So we analyzed 5 protocols, including usable patterns. we extracted reusable building blocks from these reusable patterns. And this kind of reduced the verification efforts much cheaper. We argue that this work can potentially impact on verifying other database methods. Specifically, some of the building blocks that we have are actually in wide range of database control protocols, such as constructing a structured tag using reliable workflows, which is quite common in database control protocols. Similarly, new building blocks can actually be added to kind of broaden the. Thank you.
Excellent. Thank you. Questions?
Thank you. Can you hear me?
Yeah.
Yeah, sort of an excellent talk. So my question is there any specific reason you haven't used Paxos for the consensus? Because this seems like a reliability problem, right? The Byzantine atomic
Yeah.
clock.
So we didn't so we didn't define these protocols. So the thing is that in Paxos is different from that case. Paxos from day before Paxos from the protocols. And so the idea was to kind of try and verify the recent targets and so on. So I think Paxos has formally request specification.
Yeah, that's it. So Hedera Hasgraph, has been verified using Coke,
Yes.
right? So how does this compare to, because you're using TLA plus?
Yes. So the top specifications are, with my experience, are not that closer to the implemented one that I just taught. So you can actually not generate traces of those specifications. But the plus point there is that they also have the line of switch, whereas there's one we talked about cases there. And I think our objective was not to first verify hardware, but since we saw these reusable patterns and thought we can actually add hardware to this without performing much
Any other questions?
It can work out kind of like I like the tree of invariants and I like the pose. What was the hardest part? Do you have invariants where it's like, oh, I'm not sure how are these purely automated proofs or do you have a lot of hand?
I think proofs are all handwritten and the invariants also we had to identify all of them. And plus,
I'm just wondering where the what were there road, what was the hardest thing in were there particular ones that were where something really was difficult?
My procedures and PMVs were I started writing a proof for the direct safety and then it failed. It was not inductive. And at some point, I had to kind of I need to identify an event that would kind of meet those proof. And then I would identify that. And this is not the most optimal way one can prove it, but the best procedure that to kind of identify things.
Thank you. Any other question? I have curious about something that you wrote in the conclusion. You said something like proof effort reduced by almost 50%.
Yeah.
And this is compared to what?
So this is compared to, I compute that based on size of two plans. This is what we require. If one had to actually prove each of them from scratch. That means you just simply multiply each of the number of two plans required for each of the building blocks times the number of times that building block appears on these 5 buildings. And so you kind of add those.
Okay. Any other questions? So my final question is another comment that you have in the paper about the proof compared to, I think that you are comparing that to a proof in Postgres. You said that the proof in PLA plus are lower level and closer to implementation. What are you referring to there?
This is in a relative sense I'm talking about, but compared to talk or or IVS, because there's one has to do kind of specific numbers and how you can define these protocols. And in that sense, I meant can actually, this is a transition system, and conversions, and you can actually generate executions where you have action, you go sequence of action, which kind of you can map to the sequence of actions in your implementation. That's okay.
Okay. Any other question? Thank you very much. So let's change again the topic. Now we are going to talk about verification of the writing systems, and in particular, an algorithm that is called identification. So our speaker for the last talk of the session is Maria Julia Diaz Lima, and she's going to talk about verification of anti-unification algorithm in web PBS.
Um, uh, I will be presenting the verification of an anti-unification algorithm in PBS. This work was developed by Marisa Rincon, Tainara Ariel, myself, Mariana Mustafa, and Camille Victor. This is a group involved in real. It's one. This is the outline of the presentation, and I will be starting with operational reasoning. Considering SMT terms and sigma and substitutions, we have expressional problems that follow. First, we have the quality check, then the matching, which is whether this is a sigma such that sigma applied to S is equal to T. The unification, which is if it is a sigma that applied to S is equal to sigma applied to T. And then for unification, exists the sigma that applied to the term R and that applied to the term R is equal to 3. For unification, its goal is finding a sigma that applying to S and T, we can identify them reaching a common element between the two after our substitutions. And to identify two expressions, we replace the variables by other expressions. As an example, considering x and y variables and a and b constants, and f a functional symbol to identify f of x and f of b and f of b and y. We have as a solution that x replaced by b and y replaced by a. So another example is considering identifying f of x and y and f of b and y. A solution in sigma would be replacing x by or as here represented by gamma, x by b and y by b. But we can say that sigma is more general than the gamma because there is a substitution that applied to the sigma, that is the gamma, which is y replaced by b. The relevant questions are on decidability, the unification type, the correctness, and the completeness. And when it is decidable, we can question about the complexity of this presentation. And considering this syntactic case, we know its type to be unary and its complexity to be linear, considering the adequate data structures according to this group. Here we have the timeline of the formalization of equational reasoning. In purple, we have the formalizations. which begin with nominal unification in Isabel, then you see matching in Coq, nominal unification in PBS, nominal verification, and nominal matching in Coq, nominal unification and AC matching, and AC unification in PBS. So the last one here is this one, which is the first version of the first order syntactic anti-unification formalization in PBS. Now we move on to the anti-unification itself. Here we have a brief history of anti-unification with the selected books. Here we have a few examples of applications of anti-unification, which include searching reality hypothesis space in inductive logic programming or logic-based machine learning, preventing bug-ring misconfigurations in software, detecting code clones, and searching insertion schemes for efficient parallel computing. The goal of anti-unification is that given two expressions, we want to find the expression here represented by R, which if we apply this substitution, we get X, and if we apply it to the right side, we get T. This is the representation of a generalizing. As you can see, it is just the decomposition of F, and we have a pair of arguments that is given. Here we continue decomposing, and on the left side we have a decomposition of the same function F, and the second argument in this new pair is B, because it is fixed on S and it is also fixed on T. In this step, we have merged U and V because, as we can see, they are represented as the same triangle in each term. So we can represent them both as U. So this way we get a least general generalizing, is a generalizing which we cannot do anything because it is already the least one within them from this representation. So this work was done on syntactic anti-unification, which I will be talking about now. For our verification, we have as our terms the variable, the unit, the pair, and the function, the application. We used label equations, which we called AUTs, which given an I smaller or equal to the total of equations, we have a term S in position I associated with term T, also in position I, labeled by a constant X in position E. The type to which we have applied the algorithm for the anti-unification is what we call a configuration, which is a triple that has an unsolved set of equations, an solved set of equations, and a set of substitutions. This configuration has a few constraints. The first one is that the labels in the union of the sets of unsolved and solved equations have to be different, and no repeated equations can appear in the solved equation, and no label in this union can belong to the domain of the substitution. We also have that the solved equations have a left and right hand side that cannot be headed by the same symbols. Otherwise, if it is headed by the same symbols, we can still apply our rules and stuff. So here we have our inference rules. The first rule that we have is the decompose function rule. Here we have the same function symbol on each side, and we remove this symbol and add a new label of a fresh variable, and after the substitution, set the substitution of the former label by the functional symbol applied to the new label. In the decomposition of pairs, this shares the same idea that as the function of decomposition, but we decompose it into two new elements, associating the first and the second elements of each pair and assigning to each a new label. The substitution then is the initial label by the pair of new labels. The solve repeated is the case in which we have an equation that is already in the solve part, and it already has the label called x called x prime, and this is in the set of solved equations. So what we do is we add the substitution of x by x prime, and in the solved non-repeated case, in which we don't have this solved yet, in the set of solved equations, we don't have this equation there yet. So we just put it in the solved equation set, and then we don't do anything with substitution. In the syntactic case, what we have is that we have two terms that are the same, and this is not decomposable or solvable in any other way. So what we do is that we add to the substitution the substitution of x by this term that we have, that is x. So we have here an example of the application of this rule. First, we have that the same functional symbol is on both sides. So we apply the compose function rule. And on the second one, we have two pairs on each side. So we apply the decompose pairs. And the following two cases also follow that logic. The first one has the function in both sides. So we apply the composition functions, and then we get again the two pairs. So we also apply the decomposition of pairs. And so we start with the first equation that we have now on our set of unsolved equations. And we apply to it the solve non-repeated rule because it is not in the solved list yet, so we can add it there. And next we have as our first element here something that we can apply the syntactic rule to it. So that's what we do. And next we have an equation that is already in the solved part. So we apply the solve repeated rule to it, and this what we have here that x is replaced by all of this is our generalizer. So if we apply this substitution here to z, replace this by c and z by d, we get each side of our equation, which is over there in the top. You can see this is also the same as we represented here. So our generalizer is that generalizer, which we showed here, but this is by the application of the rules. We get this in the rules. So Now, this is how we have verified these groups using PDS. Also, I have used some pseudo code because I think that would be a little bit clearer than showing what we actually did on PDS, so that's a little harder to understand. Here, the type of a configuration, which I have mentioned in the view before, is represented by a list of AUTs. It is represented actually by two lists of AUTs, one for the solved part and one for the unsolved part. And the substitution has this type in nice, which is a predicate that tells us if the substitution actually has the shape we want it to have. And the predicate for valid configuration, which states the notion expressed in the definition of the configuration. Here we have what we define as a valid configuration, and considering the EQS as the union of the unsolved and solved parts, we have that the variables in this union and the labels in this union have to be disjoint. And the cardinality of the labels in this union and its length has to be the same. Also, the domain of the substitution and the union of the labels of this union and the variables of this union has to be disjoint too. And all the solved equations have to be solved equations. They can be equations to which we can apply the rules, otherwise our algorithm would be wrong. And the solved equations cannot have repeated rules, repeated equations, because if it did, we could could be an error because we should have applied the solved repeated. And so the unsolved and solved lists of AUTs represented solved and unsolved equation, the configuration. Configurations are deterministically classified according to their durability type based on the type of their had unsolved AUT, represented by match backup, match backbeat, and match synthetic and match solved, which are predicates that determine this. So let this be our um, our element that we're considering, and that is the head of the unsolved list in a configuration. Then we have this type match deck f on. If this element has a type match deck f, which is specified by the left-hand side has to be an application, and the right-hand side also has to be an application of a function. And functional symbols have to be the same, so that we have that format that was described in the inference rules in the team. So the configurations all have their own type for each rule. And when the unsolved part is empty, which would mean that our algorithm has ended, we have the normal configurations. Which they just us to so the identification algorithm is we use the inference rule specified as function declarations with parameter configurations if that is the type I mentioned that is on. And the solved rules, they were integrated into a one solved rule with this parameter configuration type. And to automate the proofs of termination, configuration, validity, and correlation of niceness of the communication algorithm, these properties were encoded in the types of the functions representing the rule. Here we have an example, which we are considering now the type of the function of the composed function rule. The input of the input type of this function is the configuration of the type match that I've called, which is a predicate. It checks if this input is in this format, and its output type is considering C, the initial configuration, and C prime, the final configuration, the input and the output configuration respectively. Then the type of the final configuration is given as first the here the first one indicates that the preservation of the tail of the unsolved lists has to be something here. And the size here is to guarantee our termination. So all of our functions that determine something that has a smaller size, it helps us with the determination of our algorithm. And the last one is that the label that we are assigning is the old label, the label from the initial configuration, that is replaced by something in the shape of a functional symbol applied to our new label when we apply this function. So for the specification of the algorithm itself, it was defined as a recursive function of type valid configuration for valid configuration. Its measure is the size of the unsolved part of the initial configuration. So this is why we use this size here, so that it ends. The algorithm recursively checks the type of the head of the unsolved part to apply the respective inference rule. By restricting the types for the functions and specifying the inference rules, we name them that f, that we solve and sync. The guess automatically proves into unified termination, and that every output of the configuration algorithm fulfills the valid configuration predicate. So here we have a few auxiliary lemmas about invariance and configuration preservation that we used. The first one states that a substitution does not change a term. So if a term is in the range of our within the range of final substitution of our initial substitution, sorry, and the variables of the curves and the labels of our initial unsolved part of our initial configuration are disjoint, then we can say that the substitution of our final configuration over the current T is equal to the substitution of the initial configuration over the term T. Then we have this second lemma that states that the domain of the substitution of our final configuration and the variables of the unsolved part of the initial configuration have to be disjoint. Okay? And then the third one, we have that the labels of the final substitution, the solved list of the final substitution, and the variables of the unsolved part of the initial substitution have to be disjoint. This we use this because the verification depends on this technical lemmas. So as we can see here, the syntactic part, it depends on all three lemmas. So and the solve our rule that we created depends on our first lemma too. So and no previous lemma was required for the completion function composition of pairs. And the solve rule, it depends on simple conditions. The proof of the Thomas theorem is stated below, and it follows by induction on the size of the configurations and case analysis. Let's see a configuration. Then the final configuration computed by our algorithm has to follow this. It has to follow this, which means that for any AUT that we have that belongs to the unsolved part, we have that there is that the label applied to the final configuration, the final substitution uh, and applied to this function of the left side and applied to the solved part, on the left side, because sort of imagine it as a tree. So it has two sides, the left and the right side. So if we apply the substitution to the right, we have the result we want. And if we apply the substitution to the left, we also have the result we want. So in that extent. So this is the idea. So
Maravilha.
so this is the formalization in numbers. The syntactic one was the largest one because we had all those dependencies that I just showed. And yeah, it had a lot of dependencies because to show that that the preservation of the constant var or unit that we are replacing our label with, we need all those lemmas. So that increases the complexity of our proof. And the solve R rule also depends on that preservation lemma 1 for the substitution of the x prime label by the x label. So this is also this also increases the complexity, making them the two most complex cases we had. So for conclusions in future work, we're currently considering working first on A and C, which is associated with continuity, but currently we're finishing the syntactic case. But these are the only two cases we're considering. And for conclusions, although anti-unification has become an increasing interest, most verification of anti-unification algorithms has not been explored except for the simple synthetic case, which is what we did here. The development of procedures to solve anti-unification model theories is crucial. And only recently, anti-unification model absorption, commutativity, and absorption commutativity symbols have been addressed. Procedures combining such properties have been shown to be challenging from theoretical and practical. That's it. Thank you.
Thank you. Time for questions. So one question I have is,
is the algorithm that you prove executable? Can you execute that in PDS-IO? Can you run that in PDS-IO?
Yes. Yes.
It is? Excellent. Another question? So I'm curious about the representation of variables. Are you using the nominal framework or do you have representing variables using, I don't know, numbers? I mean, how do you represent variables in these algorithms?
We're using the nominal presentation.
You are using nominal? Okay. Any other questions? Okay, sound the speaker. Thank you.
Thanks, everybody, for attending the first part of today. We're going to be on lunch break until 1:30. There's plenty of places to go get lunch. There's a cafeteria downstairs. We'll be back at 1:30 for the next set of talks. Thank you.
Sections of the NFM, NFM, and this section is about verification and was about formally covered invariant chemical properties of central form. So the integral to the same.
Thank you very much. So before I start, I will just launch the analysis. So if it fails, you can complain at the end of the talk. And since it takes a little bit of time, don't. We'll see. Okay, yeah, it's starting. Okay. Okay, everyone. So yeah, before I start, this is a joint work with Elias Khalif and Mazen Fahoud, both of them from the Virginia Tech, not too far from here. But both of them are from a control background. And Elias is not here, but he's a PhD student, and he did 99% of the work. So here we try to answer 3 questions. The first one is so everything is rooted at code level. Like, how can we prove properties at code level for like a controller? But what interests us is to express properties of the closed loop. So this is a little bit a challenge. So how can we do this? How can we express closed loop properties like systemic properties at code level? And to do this, that will be the first part of the talk. How do I mechanically express closed loop properties attached to a controller? A second concern is if you look at dynamical systems in general, they are often either nonlinear or subject to like exogenous disturbances, noise. And so the second concern is how can you consider this when you perform the verification. And for that, we will rely on a tool used in control, in robust control, called IQCs, Integral Quadratic Constraints. And we will see how we can rely on IQCs within this framework of deductive verification. That's what I use for verification at code level. And the last item is all this issue between reasoning with reals or reasoning with floats. How can you deal with this when you want to prove properties at code level? And to do this in this work, we proposed a kind of double modeling of the properties. A first layer where you forget about floats, you prove it valid for reals, and then you integrate floats in the mix. So let's jump in with the first topic. So everything will be illustrated by code, so I hope you can follow it. We are concerned by dynamical systems like the very nice signaling block on the right. Those systems have like an internal state, and typically the kind of code you have is something like that, like a step function if you want. you call the function with a pointer to a structure that represents the internet state of the node, and then you provide some inputs and you provide the pointers to outputs because there might be multiple outputs. So that's why we use pointer for this. So another way to see it is to like extract the state, to see it like explicitly as something from the outside. And then typically for linear controllers, at least, what is relevant is Lyapunov functions. So quadratic invariants written like this on the predicate line. So in pharmacy, in a tool to perform verification of code with deductive methods, the team that developed pharmacy developed a ACSL specification language for C. And here you have an example of some contract. In annotations, you can define the predicates. Like here, it's an invariant, a quadratic invariance on X, the real value, and L, the upper bound of that ellipsoid. And then you express the fact that this Lyapunov function is an inductive invariant. If you require, so if you enter within some bound 1, and then after the execution of the step function, you should be still in the same invariant set. So that's how we do it. But here it's a little bit naive because everything is accessible. In practice, we want to work with closed loop systems. So in a closed loop system, you have to distinguish something that is the controller or something that is the plant you want to control. And in the past, what I did was I just assumed everything was code. Everything is discrete time, so everything is code. So I can produce the code from this Simulink model and have a step function for the controller, a step function for the plant. And I can like, it's a little bit fake, but I can build a kind of closed loop function that combines the two and annotate it with a contract. So it's the same kind of work, except that here I cheated a little bit because I have this extra void plant function that really doesn't exist in the code. And I have this fake void closed function that also doesn't exist. So if what we dream would be to take the actual C code that will be executed on the final platform, and then have ways to express this closed loop property just for this function. So that's what I will try to explain to you now. So the first concern here is that we just have at this level, we just have the memory of the controller and its interface with input and output, but we don't have the plant at all. So the first thing you can do in pharmacy is you can add a ghost parameter if you want to your function. So it's not a real parameter, it's something that doesn't exist, but you can reason on it, like if it was provided to the function. That's the last line in green, ghost float mem plant. And then the question is, how do you model the plant dynamics in the predicate world? So to do this, we propose to have two predicates, two logical functions. One of them to express the update, like the step function of the plant, and one of them to express the output. And both of them can be written like in math on the right-hand side of the equal thing. Then you can plug that together. The idea is to attach, now that you have at the level of the controller access to this ghost feature mem plant, you can have you require the input to the controller to be the output of the plant. And now everything is defined, so you can do this. And in the ensure statement, what you want to do eventually is to say that a kind of invariant of the closed loop system will be preserved once you perform the step functions. So with this line here, I don't know if you see my post, yeah, that's how you define like the next state for the plant. And then you finish by just adding the same invariant we had before. So you have to define your quadratic invariant, the subline here. And then you put it both as a require, as we had before, like you require to be in the ellipsoid, and you require to be in the ellipsoid after the execution of the code. Here, the invariant is a little bit more complex because it's defined both on the variable. You explicitly mentioned the fact that it's defined on the state variable of the plant and the state variable of the controller. So by doing this, we can really embed the actual code of the controller. We do not touch the C code at all. Everything is in the annotation work, but we manage to capture the closed loop property and attach it to the code. So that was the first part. Then let's speak a little bit about IQCs. So I don't know how much you're familiar with this, but I don't know when it started, maybe in the 2000, I would say. So I think it's Anders Schanzer and Megretsky who wrote like this seminal paper about that. So it's a control theory tool to deal with uncertain systems. So it's connected to robust analysis if you want. So I try to summarize this in a couple of slides. So for the expert, it might not be perfectly accurate. So I apologize for this. So in most settings, you have a first like requirement. The systems you want to analyze have to be expressed in this LFT form, linear fractional transformation form. So we'll see that next slide. And also another requirement is for your properties of interest to be expressible as quadratic inequalities on input-output relationship. So that's the requirement. So if you don't satisfy this, it's hard to apply the tool. But once you have this, more or less, you can remove those elements that are uncertain and just model them by these quadratic inequalities. And then you can do like the usual approaches of like stability analysis, Lyapunov function computation so you use your usual SDP solver, semi-definite programming solvers, to do your analysis. And also an interesting thing for us, computer scientists, is that for us, I mean, I don't know how much you're aware of control, but in control, in the linear setting, you have like these frequency domain analysis tools that are really strong. I mean, they are really powerful. They can claim a lot of stuff, but they do not make a lot of sense to us at code level. And here, what is great here is that there is a lemma, Kalman-Yakupovich type of lemma, that connects frequency domain and time domain properties. And this is really like the root of this IQC framework. So more or less, to make it quick, thanks to IQC and KYP lemma, you have a kind of translator from frequency domain properties, time domain properties that you can use here. So all of this is control theory. But if you want to rephrase it to someone who just speaks like abstract interpretation, this is a kind of sound over approximation of parts you don't know really how to model. Like they can be like nonlinear parts, or they can be noise. So how is it working? So on the right-hand side, I try to put a system in an LFT form. So in an LFT form, you want to distinguish a linear part of the system, that's the G block. And everything that is nonlinear, you hide it into the delta operator. So if you have this, and you have some requirements on delta, it cannot be arbitrary. It has to be a nice delta if you want. What is the uncertainty set for us? It's the M delta set. The list of pairs, P theta, that satisfy this, okay? So you don't really, that's the object of interest if you want. And if you have such a delta, you know the delta function, but you don't want to have a perfect and exact characterization. So you will introduce an IQC, an abstraction if you want. What is an IQC here? It's the pi operator, and it's composed of this psi and this s operators. So you have to, using an IQC here, amounts to propose your own psi and s, such that this is verified. So you build this operator pi, and you are only interested in the list of pairs pi theta that satisfies this inequality. Okay. And by definition, I mean, if you use the proper IQC, the M delta would be included. The list of pairs of the exact operators would be included in the list of pairs that's the abstract operator captures. So that's the idea of IQC. And how is it used? So typically in control, since they are really strong with linear systems, when they have deltas, they don't know what to do. So by hiding the delta and capturing it with an IQC, then they remove the difficulty, and then they have ways to use this pi operator to do the analysis. And sometimes it's also a good way to capture noise, like if you have like wind, these kind of things, it's how you can model it as well. So you can speak about IQCs for like a week, but there is, if you want, there is a large library of work. You have different flavors if you want of IQCs, whether they are finite dimensional, infinite, whether they capture like a discrete sum or a continuous sum. Anyway, and what is great is that for your systems of interest, there exists already like a proper choice of IQCs. Like if you know that the system is subject to some time delays, okay, but you know that it's not arbitrary time delays, that those are bounded. Or if you know that there is a saturation after your system, then you can use an IQC specific for that and capture that specific noise. So just as an example, I won't take too much time here, but if you have a system where a component has a linear time varying perturbation, then you can use what is written on the bottom of the slide. You can use this specific IQC to capture the fact that the noise is bounded by alpha. So an LTV perturbation is something like this, where delta is bounded. And that's, I mean, with this specific IQC, you can capture it. So how do we do this? It's not too difficult. What we do is we need some parameters. The delta was bounded by alpha. So we introduce a parameter. It's a fresh variable that would be bounded here. And then you remember the psi and the S operator defining the IQC. So more or less, my augmented system here, H, amounts to capture the S part. And the piecewise IQC thing here is more like my psi function. And that's what I have here. I have another quadratic term here that needs to be positive. I have some function here that defines the S operator. And now I have as a require the fact that I'm only interested in systems that verify this IQC. So here it's used to model part of the planes. And let me finish with the idea of the double modeling. So again, I don't know how much you're used to prove stuff with floats, but to me, in deductive methods, there are two approaches. Either you rely on a very precise and exact axiomatization of floats at the level of like proof objectives, or you instrument contracts to integrate floating point errors. So let me just see why I don't believe in the first method. So if you take like the simplest of the linear setting here, it's a linear function that computes 2.5 times x plus 0.7. So pretty simple. You know that it requires x to be positive, and you want to ensure that the result will be positive. So I hope you trust me that it should be valid. If you send that to pharmacy, so you use minus WP, that's the weakest precondition engine, the one that does this reasoning with deductive methods. And here I'm saying explicitly that I want the reasoning to be performed with reals. So as if it was not floats, but just reals. So here by doing this, the proof objective is only manipulating real variables. And here in like 8 milliseconds on my computer, it's proof valid. So we are happy because it's a simple system. But now if we remove the WP model real option, then since those values are floats, they would be modeled by floating point numbers. And here it fails. So on that example, pharmacy is not able to prove automatically that it's valid. So I don't have like a very deep understanding of on why it's not working, but if we ask specifically for the ROC outputs of the two proof objectives, In the first setting, just with reals, it's just 100 lines. And with the floats, for the same kind of problem, it's almost 2000. And I'm not including all the dependencies of the axiomatization of floats. It might be much, much, much bigger on the second element. And as well, if you look at those like lines of theorems are the last lines of those two rock files. So in the first one, we see like a very naive R positive, blah, blah, blah. You have the theorem that you want to prove. But in the second one, since it's exact axiomatization of any kind of floating point operations, each time you do an addition, a multiplication, they have some rounding. Some rounding is involved, and then it's a mess to do any kind of thing. So I'm not saying it's not a bad choice to use this, but in my opinion, you cannot really trust automated solvers to do anything interesting on this kind of things. Okay. So what we rather recommend is to combine like abstract interpretation and in this kind of methods to instrument the contracts to integrate floating point errors. So here on that specific example, I used my tiny tool here. I don't know if you can read it, but basically I analyze the code with my my solver, and it returns me that here I have a noise, the order of 10, negative 9, negative 6 error for the outputs. Okay. So on this challenge, where now X is bounded between 0 and 10, I know that the error is like this, at most this size, and I can instrument the contract by introducing a fresh variable. Here I call it n. I want n to be anything between -1 and 1, and that's the integration of the noise in the output. Okay. So I'm saying that the output, I don't know really what it is. Okay, n can be anything, but at most it could be either 1 or -1 times the noise I computed. So here the challenge is slightly more difficult because now you have an additional variable in the mix. But for pharmacy, it's as quick in this very simple example to prove that it's valid. So in my opinion, it's more relevant to use this kind of method to analyze your system. So you always use the WP model real. You always work with reals, but you need to integrate your the floating point noise within the contract. So I don't know how much I need to develop this, but basically there is something called the standard model of floats to capture the floating point errors. And basically, if you do the sum of two floats, you get more or less the sum of the two numbers they represent, but some noise that is proportional to the result. And this noise is a unit in the last place of 1, depending on the format you do, whether it's simple floats or double. And for multiplication, you have an additional error for denormalized numbers. And basically, it's very quick here to instrument code to do this, especially for the program that interests me that have no loops. So we don't have issues with computing fixed point with floats. We just have some bounds on the input, and we need to compute one step function and obtain the resulting bounds. So it's not as precise as the option with ROC or with the exact axiomatization of floats, but in my opinion, it's more tractable for verification. So there's an additional issue in our context, because to make sure that what you compute is really sound, you need to ask the image ellipsoid to be slightly smaller. So I let you read the paper to know how it's computed. But that's what we obtain eventually. So basically, we have requires INV, requires IQC for anything capturing the IQC part of the plant, requires Y equal, like to do the connection, the closed loop thing. And then all our contracts are doubled with one with just pure real computation, like this real model thing, and one with the float with the additional quantified variable here for the noise. So to conclude, that's the complete framework for the analysis of complex dynamical systems. Everything is based at code level analysis. It's able to capture systemic properties of the closed loop setting. And it's the start of using IQCs at code level. And yeah, and we also deal with floating point issues. The experiments is, in my opinion, significant. We have 3 examples, and they are relatively large. I mean, large for the classical stuff we do with Lyapunov functions. So if you look at the US controller, for example, it's a 16 state variable system. So the Lyapunov function here are pretty large. And those are models with some of them with IQCs to capture part of the nonlinearities. I can show you the code of that at the end if I have time. In terms of like limitations and for future work, if the IQC is part of the modelization of the plant, it's like given, I don't have to argue, it's part of the work of the person that produced the model, so I can trust it if you want. But now it would be nice to use this to perform the analysis of the controller code. If there is some part I want to hide for the analysis, but today I don't know how to verify the fact that the choice of the IQC is relevant for my system. So here it's still something missing. And I still have issues with reproducibility. So in those examples, it works, but since we rely on very complex solvers to do this, it's a little bit fragile, and it would be great to have ways to exhibit more like ingredients of the proof to have like a kind of easy revalidation. And for the moment, all the annotations were done like manually or almost manually, so it's a limitation of the work. So let me just show you. So during the talk, everything was proved here. Okay, so on my examples. And if you want to have a look at, so it's okay if you cannot read it, but like here, you have it's not easy problems, okay? Here you have the first one, the first block is the ellipsoid of my system in dimension 12 here, or 11. The second one is one of the IQCs we use. Here we have the updates of the plant model. And here the contract, so you have the bounds on the parameters of the IQC. You have the initial ellipsoid. All this block is the IQC, the use of the IQC. Then you have the wiring of the Y, and you have the double contract, the one where you compute the outputs, and it ends. The last line is the image ellipsoid, and the same thing with the quantification of the errors and the updated bound. If you look at the right, the very last part of the last line, it's a little bit ugly. That's the change of the bound of the ellipsoid. So maybe I should stop here. Thank you very much.
Thank you, Pierre. Questions?
Okay, very nice talk, Dirk. So I have a couple of questions. The first is the 2 round of error models that you showed. Where are those formalized in your framework? Is it in ROC?
What do you mean?
The floating point error formalization you have for the addition and the multiplication, are those like formalized and proved
Here?
where? So where is Pharmacy taking this information?
You mean the bounds, the noise? Yeah. No, this is manual. I use my own tool. So yeah, this is where it would be better to be more automatized. Basically, the control person has to first do the analysis, find the Lyapunov functions, etc. Okay, I'm just checking that at code level. And once you have the Lyapunov function, it's easy to project it to each dimension. So you get the bounds on X, Y, Z, etc. And having those bounds, you can run like my own floating point analysis that computes this tiny error. And then we write the second contract.
But yeah, I mean, you can also use some like floating point analyzer.
Yeah.
Separate it and that's something like right. And also I don't know, when you show the example, that you don't want, I mean, for you, it's not a good idea to map directly floating point into, to use the floating point engine behind Promaxi. So there has been some effort made from Promaxi people to try to reason with flows in a sound way, maybe using some SMT solver or speed vector, or maybe using approximation. So you don't have to do this work,
Okay,
there
so
are
just
things-
this, like even the real version, the one on top, no tool today except mine is able to prove it. Like AltaGo, D3, CDC5, none of them is able to prove it. So here what we have, that's the work of Pierre Hooks, if you know him. What he did is he integrated in AltaGo a sound sum of square optimizer, and everything was proved in a rock to show that the now it's integrated as a cock proof, as a rock proof. So there we have a very strong solver. So I showed you initially, like my very simple linear problem was not provable directly. How can you have this proved automatically with current solvers? Including, I mean, if you, in addition, you add all the axiomatization approach, I doubt it will be working. But I mean, it should at least work for the first version with the linear setting first.
No, I was asking if you know if in Promaxi there has been some effort to try to reason on floating point, but not in a symbolic way, or maybe with it better, but maybe using as you did, like some approximation, so you don't have to
Like what
manually write the round of errors, but take care of it.
I know, I mean, it's on the table, but I don't know if it's
fully or something.
Yeah, but it's not integrated in Promaxi.
Okay, thank you.
So,
I think that we don't have any more time for questions, but thank you very much.
okay,
Thank you very much,
thank you.
our speaker.
Cheers.
And in the second talk of the session, we will have Sumio Moriuka talking about the formal verification of composite field multipliers and information political secure radio communication in space.
Just for introduction, and my name is Sumio Moriuka. I'm from Japan. And so basically, so my talk is related on the security of the radio communication system. So this is the structure of my talk. And the first, and I will introduce my motivation, and also I will explain what information theoretical secure protocol. And also in the next, I will explain about composite field multipliers and key challenges in the verification. And finally, so I will explain our proposed method. So there's a lot of the complicated theory in the background. That's in this talk. So I will talk about the overview, and so avoiding the I will omit very much detail or just mathematics theory or something else. So So here's the motivation, and so the first of that. So I myself working in a Japanese new space company, and which developed the sounding rocket. Which developed rockets, and also so our company develops the next generation satellite systems. And actually, so this is the photo of this our company. And so our company is located in the North Islands of Japan, and so we're developing satellite launcher. And since the next year, so we have started another project, and so actually we are trying to develop so broadband from D2D. D2D means direct to device, and so we develop the next generation the D2D communication satellites. And so this the basic research is funded by the Japanese government. And so in particular, so this satellite concept is very unique, and we try to make the high density information file, and we will try to provide at least 10,000 to 100,000 picosats so very narrow space to construct a very large scale antennas. And by constructing this kind of antennas, and we expect also D2D communication, so broadband D2D communication be possible. So, and then, so anyway, for this kind of spacecraft, so needless to say, so radio communication is very critical, and so we have to control these spacecrafts from the ground. And for example, for the rocket, we send control normal commands, and also so we have to receive the location on data and that kind of control status signals from the rockets. And also in the satellite system, so we will use many wide radio communication channels. And so not only from the service or the peering, but also the spacecraft control links. And so in this talk, I'd like to focus on the control communication link between the spacecrafts. And basically, so for this kind of control systems, we cannot use the optical link. So we have to use the radio link. And so also, so this spacecraft control channel is very critical for public safety, and also keeping the stable operation of this kind of spacecraft. So we want to achieve the highest possible security, and also error-free implementation for this kind of communication system. And also, so just as a background, we have to get an approval from the Japanese government to price these kind of systems. And so there's many discussion about how much security is necessary for this kind of control system. But so anyway, so if we achieve the highest level of security, that is sufficient. So this is our motivation of this research. And so in the other companies, so we have proposed a secure protocol for spacecraft control. And so for designing the protocol, we identify some security requirements. And so these are very standard, not limited to protocol. And this the security requirements consist of two things. The one is confidentiality, and the second is integrity. The confidentiality is basically achieved by the message encryption. And this confidentiality means that only the intended receiver can access the message. The second property, the integrity, and that is achieved through the message authentication. And this means the receiver ensures the data integrity and the sender authenticity. And so in this particular protocol, so we want try to achieve this one, the information security. And this is different from the standard for the internet security. So in the most ground systems, the security level is like a computational security. And but so we want to achieve the much more higher security level. And so this information security is theoretically the highest security level, and so this means that the security is unbreakable, even with infinite computation power used. So this is much stronger than, for example, quantum pattern is. So this information security cannot break even if you use a quantum computer or some other technologies. And here is our proposed protocol, which is presented before. And so basically, so this protocol and so the input of this protocol is the message, and the message consists of the several blocks, and so one block, the length of the one block is n bit, and so the upper part is a sender operation, and the lower part is a receiver's operation. And the one unique point is the sender and the receiver share the same keys in the key storages. And the point is the key is changed in every message. So that is the difference of the standard security systems. And the point is that how much the key storage is, and so for the space control systems, the total amount of the message in the lifetime of the spacecraft is limited. So, so we have estimated that for the rocket, only several hundred megabytes is sufficient for this kind of stage. And also in the satellites, and several terabytes of the key amount is sufficient for covering the entire spacecraft. So anyway, so this sender and the receiver share the same set of the key, and so this sender and the receiver they use the fixed keys by using the GNS receiver. And what I mean is time information, which is basically the same between the sender and the receiver, and is used to access the key storages. And basically the key synchronization achieved by this DNS receivers by the GNS receiver. So anyway, and the first message is encrypted by the key which was obtained from the key storages. And but this encryption operation is very simple. So this is just an extra operation. And after that, for doing the authentication, we attach the authenticator, and so this is computed by another key. And in the receiver part, first we can decrypt the message, and also we compute the authenticator, and so we check the authenticator is correct or not. And so the point is that for computing the data authenticator, so we use repeated multiplication over the large and finite fields. And in this case, the bit widows of the multiplication should be larger than the 128. And also, for this as a multiplication operation, so implementation in hardware is preferable, and because of the speed and the low power. And so because the most of this operation consists of the finite field multiplication, so the correct implementation of multiplier is very important. That is a key issue. And so this is some outline of the proposed protocol. And but it's one point I want to mention is that so this kind of the finite field operation is very common in the speed area. So not only not limited to our protocol. And actually in the authentication is the ground systems. So this kind of field multiplication is used for the authentication operation. So our technique can be used for implementing ground systems. So that's a very, and that's our motivation and also a background in protocol. And so I want to explain about what the composite field is, and also the key challenges in the verification. And so there's a lot of some mathematics in the background, but so I omit the complicated things. And but here's the basic of the finite fields, and so finite field is a number systems which is closed under the addition and multiplication. And the smallest field is here. So that is called the prime field. And so this smallest field consists of the two elements, so 0 and 1. And so we can define on this field for addition and the multiplication, and that is shown in that table. And so in the gate level, that additional operation can be implemented by XOR gates, and also the multiplication is implemented into the AND gates. Okay, that's very simple. And the point is, so we can make the larger field by some mathematical operations. And so from that prime field, we can extend that one to n-bit field which represent n-bit values. So that mathematical operation is called an extension. And in other words, so we can make so that GF22 and that kind of field from the prime field by the field extension operation. And so the composite field is a finite field that is constructed by the repeated multiple extension from the prime field. And the point is, so we can use this extension in a different different way. And for example, so if we want to construct for 8-bit fields, so we can make that from the prime field. And so there is a different way of constructing that kind of 8-bit fields in a different way. And for example, so we can extend this prime field in a single extension, and so we can make this field. And in the different way, so we can extend this field to this field, and also by extending this field to this field, we can construct an 8-bit field. So the multiple composite field may be just for the same details. That is the point. And so this slide shows why so we want to use this kind of a composite field. The merit is very simple, and so we can shrink the circuit size, and also we can reduce the power consumption as a hardware by using the composite field multiplier. And actually, here is an example of the composite field multiplier. And so this is a single extension field multiplier, and that gate size is shown here, shown there. And so here is also implementation of the composite field multiplier. And that's actually as shown here, the circuit size is much more. And so if we proper proper extension, so cutting is that kind of circuit size is different by selecting the extension of the way, the extension of the selection of the extension. And if we choose a proper extension, so we can reduce the circuit size significantly. So that's the point. And so I'd like to move to the verification of this kind of the multiplier. And so verification, so as you can see, the verification of this kind of composite field operation is very defined in the integer operations. And so here is a number representation of the finite fields. And so basically, so a field elements representation have two types. One is exponential representation. The other is bitwise or binary representation. And basically, so this is a explanation for representation. And basically, so this corresponds to the, so for example, so decimal or so hexadecimal representation in numbers. In the other words, so this is a word level representation. And so this is a binary level representation of the field elements. And as you can see, so in this table, and so there is no there's not obvious regularity in the representation. It's very difficult to understand. And so as a designing so this kind of multiplayer circuits, making the test correct test case is so not easy task. And so this is a so it's a general issue in this field, the finite field operation implementation. So so this slide explains for the single extension case how the verification is done. And the point is, so for the single extension multiplier, the circuit structure is very regular. And so here is an algorithm of the single extension to multipliers. So as you can see, the algorithm is very short, and so this is very simple. And so that is a straightforward implementation of the hardware. And so that is that is basically a straight connection of so this the group part this operations. And so as you can see, so this part is very simple, and that's simple to AND and shifting, and the extra operation is performed in the one iteration of this loop. And so in the RTO level, and checking the implementation, the hardware implementation is rather simple, and that can be visually. But in the composite field case, that situation is very different. And in the composite field multiplier, the structure is very complicated. Basically, the composite field multiplier has a recursive structure. And so this is an example of this multiplier over GF 2 to 2. And so that's a composite field multiplier. And so this is a block diagram. And so this multiplier uses a subfield multiplier. And so this is a multiplier in the subfield. And so if we repeat the extensions, yes, this subfield multiplier also has a similar recursive structure. And if we use it, so if we to the proper extension, so we can reduce this number of subfield multipliers, and that's why the factor size of the composite field is smaller than the normal multiplier. But in this case, so visual inspection of the circuit is very difficult. That's structure very complicated. So the formal verification is strongly desired. So here is also existing formal verification methods, and so there are two previous works. And one is a formal verification method for single extension case, and the other is for double extension case. And the project a single extension case. So basically, the method checks the specification of multiplication in the word level is satisfied in the bit level. That is what the method did. And in the double extension case, so there's a limitation of applying the method. And basically, the two extension case, this as a proof of the correctness is done by the two levels. In the first level, subfield multiplier and is verified using the same method. And in the second, the composite field, the method that checks the composite field satisfies the definition of the multiplication. over this subfield multiplier. But there's a limitation that the both in the both extension, the same irreducible polynomial should be used in the extension. So that is the limitation of the previous methods. So I'd like to explain about our proposed method. And so in this work, so we propose an automatic formal verification method for multipliers over the arbitrary. So all the composite fields. And it's a single extension case and a double extension case it covers in the previous works. But the we try to cover all of the composite fields. And the key idea is that because as a single extension multiplier, it can be verified, it can be checked by the previous method. So we use so that's a single extension multiplier as a reference. And the key idea is very simple. So we want to compare the reference target multiplier. That's construct of the composite field. So, so we want to compare that target multiplier with the reference multiplier. That's key idea. It's very simple. But the issue is that so they are not the same on the Boolean function. Their Boolean function is different. So we cannot directly compare the equivalence of these two circuits. That is the issue. So, so main idea of the proposed method is to use the field isomorphism. And so this is a well-known mathematical property that so all the finite fields of the same size are isomorphic. And so that means so a one-to-one mapping, one-to-one function exists between the J elements. The here is an example of this such kind of mapping. And the right hand and the left side left hand side is that so addition table and of the same same the finite field which has whose size is the same. And but the actual number representation is different between the fields. And so there we can define so one-to-one mapping so between them. So this property holds all of the finite fields. So so in this work, we try to use this isomorphism for the checking the target multiplier with the reference multiplier. And the idea is very simple. And so we constructed, so first we construct such kind of mapping. Here, so I and I inverse is that kind of isomorphism function. And so actually, so we implement that function as a circuit. And then we connect so that those isomorphic function with the target multiplier. And then we compare the functional equivalence with the reference multiplier. And so that is the criteria. And also, in this case, so that isomorphic function is only is implemented only for the verification. And so additionally, so we needed to check that implementation of the isomorphic function is correct or not. So that is also the criteria 2 to 5, if you see that shown in the paper. And so by checking all of the criteria on the 1 through 5, we can ensure that the target multiplier performs a correct multiplication. And the point of this slide is that we can express this kind of criteria in Boolean level. And so I omit the details, but the so all extension fields using built on the over the GF2, the prime field. And so any criteria that can be expressed over GF2. And in the other word, we can express these criteria by using the X or and AND gates. And after that, and we evaluate the truth of that kind of criterion. And so that is the similar with the traditional verification approach. And so we do not use the conventional BDD or some other solvers because the criterion, the data expression, mostly consists of the exponents. And if we use traditional solvers, traditional decision procedure, the size of the expression maybe may grows exponentially. So in this work, we use customized tools solver to evaluate that, and that uses converting the formula into the PPRM form. PPRM means positive polarity read form. And so by using that kind of solver, we check the tools about the 17 hours. So we can to verify the correctness of the multiplier automatically rather than short time. So I'd like to conclude my talk. And so in this talk, we successfully verified a composite multiplier, and which is used for secure communication. And the future work is to extend our method to verify the larger fields. So thank you very much.
Thank you very much. Maybe we'll have time for a question. Was curious if you have thought if this kind of technique can be applied to other kind of issues in the communication of the spacecraft or any other kind of security issues in the system.
Yes. So as I mentioned, so this composite field multiplication is common and implementing the security operations. And as I mentioned, field multiplication and field addition is used in the not only our protocol but also the ground computer systems, such kind of the ASGCM and some other computations. So that's very popular. So we think of method can be used in the wide area.
Okay, thank you very much. Again,
Thank you very much.
and now we close the session with two short papers. The first of which is the formal verification of PLCs as service. And it's a talk by Ignacio Lopez Miguel.
Hello, everybody. I am going to talk about this collaborative work between CERN and GSI, which is an accelerator complex in Germany. This was the work that I did before starting my PhD at Technical University of Vienna. The idea of this work is that CERN has the knowledge of formally verifying programmable logic controllers, and then GSI asked us if we could do the same for a system that they are building. So if somebody doesn't know what CERN is, it's the largest accelerator complex in the world. It is composed of many particle accelerators that are interconnected. And then we have the Large Hadron Collider, which is the largest accelerator in the world with 27 kilometers of longitude. And it is based in the border between Switzerland and France. Then on the other hand, we have the GSI, third GSI. It is under construction in Germany, close to Darmstadt. And they are specialized in heavy ion research. And since they are under construction, they are sharing, they are And they are adapting technology from other places, and that's why they have some shared technology with CERN. So they are asking CERN to build some things or to help them to build some systems. And GSI and CERN share many things in common. For example, this safety or ultra critical systems. For example, access control systems. These are these gates that allow people to enter in the tunnels where the particle accelerators are. So they should only let the people enter when the accelerator is not running, because otherwise they could be exposed to a lot of radiation, and this could be fatal. So this is an example of a safety critical application. And then on the other hand, we have ultra critical application, which are these cooling towers, and they're in charge of cooling the water that is used in many systems at CERN, also at GSI. And yeah, if they fail, there could be some explosion or some problem in a critical in an application, and this would mean that some accelerator needs to stop for 1 year, for example, to be replaced. So this is a very critical system. And they have in common that they are controlled by these devices, programmable logic controllers. So some person has to program them in the specific language, and we need to ensure that the program is correct. And how do we do this? We don't use formal verification and also formal specification, which is sometimes even maybe more important than formal verification and more tricky. Yeah, what is the usual workflow on development of a PLC project? This is the standard workflow before doing formal verification. We have the experts on the application, which are the process engineers, so they know what the system has to do. And then they ask some experts, some developers to implement the system that they want to have. So the process engineers give the specification to the developers, and then the developers give back the product. In this case, we are using VIA Portal, which is a proprietary solution of Siemens. It is important to highlight that normally the specification is written in natural language. So this is something that we wanted to change. So we wanted to formally specify, we wanted to help them to formally specify the requirements. And then we wanted to formally verify that the requirements are aligned with the program developed by the developers. So we did this with PLC Verif, which is a tool developed at CERN. And it's almost fully automated. So you can take the PLC code and the requirement, and then you can get a counter example if the property is violated, or if you a certificate telling that the property is satisfied. So now the workflow changed, and the developers need to give the PLC program to the formal verification engineers to formally verify the program together with the specification given by the process engineers. And if there is a property that is violated, then we have to inform ESI that something is not aligned with the code, and then they have to decide if there was a problem with the specification or a problem with the code. Usually, it's a problem with the specification because they didn't specify exactly how it should be. And instead of using natural language, we propose different solutions. For example, logic diagrams, state machines, cosine metrics, or any other formalisms that I will show later. And now I want to highlight two problems, two challenges that we have in this project. And that's this usually what happens in this when you provide this formal verification service. One challenge is in the formal verification part, that the portal, as I said, or other proprietary solutions have these know-how protected functions that are very common in PLC development. And the developers use them because they are very easy. You don't need to program anything. You just insert this block in the code, and it is doing what you think it is doing. But for us, this is complicated because we need to model everything in our formalism to control flow automata, and we need to know exactly how this black box is behaving. So we need to, what we had to do was to understand completely the behavior of these black boxes, which there are many of them. That's one example. So we had to look into the documentation, then simulate different traces to really understand what we was doing, and then verify that the model that we built was satisfying the temporal traces that we extracted from the simulation. This is just a summary. It's quite long. And the other challenge that we had was formally specifying the properties. As I said, normally this was done before with simple natural language. So, for example, if input 1 is activated, then set output 1 to true. There is no notion of priorities, for example, in this example. There is no other, it doesn't tell what happens to the other outputs. And it doesn't tell you if input 1 could be also true when other inputs are true. So it's problematic. So we suggested different formalisms. For example, we can translate this simple requirement into input-output matrices. And here, for every combination of inputs, you can set or reset the well, and everything is structured. So everything is very easily to reproduce by other developers. It's easy to maintain. You avoid misunderstandings between the developers, the process engineers, and also the regulators if they want to check that everything was done properly. And formally specifying requirements is also important for other things like runtime monitoring. We didn't do that. But for runtime monitoring, you need to know what you are actually monitoring. If you don't have a formally specified property, you don't know what you have to do. You don't know what you monitor. Some other examples of formal specification, other formalisms. We can use logic formulas, also temporal formulas, logic diagrams, state machines, how we change from one mode to another mode, given some conditions. There are some other formalisms, and what we try to do is also to be aligned with the functional safety standards, which recommend this type of formalism. As a conclusion, to provide this service to a team that was not they didn't know how to perform formal verification was quite nice because they learned about formal verification. They were able to formally specify the requirements, and then they improved their code and the specification. So the results were that the code and the specification were aligned. Everything, there was no problem between the specification and the code. The code was linked to the specification was telling to do. The process engineers got a better understanding of what the code was doing, because when you get a counterexample, then you understand that maybe that counterexample is not really a counterexample, but you didn't take that into account, and then you can add it in the formal specification. And then this leads to have more trust in your code, because you are more sure that everything that you specified is what is in the code. And an important part of providing this service is to transfer the knowledge to the customer, in this case to GSI. So we spent a lot of time explaining what we were doing and what tools we use, for example, PLC Verif, for the formalisms to specify the requirements. This completes my talk. Thank you. If you have any questions?
Thank you very much. Questions?
Thank you for the talk. So just in a funny way, I thought this problem had been solved long ago because there used to be graph set and convert it to text image and then generate stuff. Wasn't is that failed completely? No, so not many people are doing this so far, and there are some universities with some tools, but it's not really automated. So the most advanced at the moment is this PLC ready. It's not really result.
Hi, thank you very much. I'm just wondering what is the relationship of the connection with like all the work in the world of like Simulink or Lust, because here we have like people from NASA that do threats, so they already try to help you to formalize natural language requirements into something that can then be embedded as like Simulink observers. And then for Simulink or for Lust, you have focusing, you have ways to produce code. And here I didn't understand really like what is the flavor of your the kind of properties you want to see. We have 15 with like the mission LCL kind of property. So I'm just wondering how this work is connected to all the work that is done here at NFM.
Yeah, many questions. So yeah, so we had this word with thread before, and we were able to integrate the thread-based language into the PLC Verif. So you could generate assertions given the property of thread. We didn't do that in this case because I think that was we started from the natural language and then we built this for the formalisms. Easier in that way. Yeah. So the difference, I think, between Simulink or the using other tools is that we want to verify directly the PLC code. If we transform it to another language, then we are not so sure that we have to verify then the transformation. It proves that the transformation is correct. And the properties that we verified in this project, there are many types of properties. For example, the one I showed, very simple. If this happens, then they have to set a reset and output. So with the propositional logic. And there was also something with this feedback function of this temporal, but we didn't use RTL, for example. It was very simple properties.
Okay, thank you.
Okay, I think it's time to move to the next talk. Thank you very much.
All right. Perfect.
So for the last talk of the session, we have Calvin Beck that will talk us about well-being formalizing this.
Right. Hello, everybody. My name is Calvin. I'm a PhD student at the University of Pennsylvania, and I'm going to be talking about our experience with formalizing LLVM in the Vellum project. So before we start, I'd just like to briefly thank and acknowledge all of the collaborators, institutions, and grants that have made Vellum possible. Note that both I and Gary are here today, so please feel free to talk to us throughout the conference. So this talk is going to be an overview of Vellum, which is a formalization of the LLVM-IR and Brock. We'll start by discussing compiler correctness, as well as the LLVM-IR and why it's worth formalizing. Then we'll discuss Vellum and the structure of the project. And finally, we'll touch upon how we're using differential testing to validate our semantics before concluding. So we're all here today because we care about the correctness of programs. And so we might have a program in some domain-specific language, for instance, here in Helix, which is a variant of the spiral numerical language with a formal semantics. And this program might be some complicated like control code for a rover, and we want to make sure that it satisfies certain properties so that the rover doesn't break down on Mars. So how do we do that? Well, we want to prove that our Helix program behaves correctly in all circumstances. The source language in our example is Helix, but it could be anything like C or Rust or whatever. And so to prove anything about our program, we'll need to have a mathematical interpretation of our language, which we call the semantics of the language. And the semantics can be implemented in a proof assistant like Rock, which was recently renamed from Talk, if you've seen that before. Proof assistants provide us with a rich logic to make sure to work with for verifying our properties. And the proofs in Rock are also machine checked to make sure that we don't make any mistakes in our proofs. So with a semantics for Helix in Rock, we could prove anything that we want about our program and have complete assurance of its correctness, right? Well, there's actually still a lot of work to do. We want to be able to run our programs on real hardware, and no processor speaks Helix or C or Rust or any of these higher level languages directly. Our Helix code needs to be compiled in order to run on the rover. And unfortunately, compilers are complicated programs. So how can we know if it got the translation right? Well, maybe when we look at the semantics of the program after the translation, we get a completely different behavior. And we find out that the pesky compiler actually spoiled all of the work that we did to verify our program. So we want to guarantee the program of our, we want to guarantee that the behavior of our compiler, of our compiled code is the same as the original source program. And to do this, we'll provide a semantics for the assembly code in Rock. And then we'll have Rock keep a very close eye on the compiler by proving that the compiler always outputs assembly with identical behavior to the input program. Our work is focused on this kind of compiler correctness problem. Okay, so how does the LLVM IR fit into this picture? We mentioned that compilers are complex programs, and it's a lot of work to write a compiler for all of these different languages, especially if we want to verify their correctness. Similarly, additionally, we often want to target multiple architectures with each compiler, and so that code could be built for multiple systems. But then we end up with this like multiplicative explosion of effort in order to support all backends across all of these different programming languages. And that's not ideal. So this is where LLVM comes in. To tame this multiplicative effort, compiler engineers have designed the LLVM-IR. LLVM-IR is an assembly-like language that can be used as a common compilation target for many compilers. It abstracts away some of the details of machine assembly languages, like the usage of machine registers. And this makes LLVM a bit of an easier language to target, and it allows for LLVM to do some of the heavy lifting itself. So LLVM implements backends for various architectures, so that all of our front-end compilers are only going to need to generate LLVM-IR, and then LLVM can handle the register allocation and data code generation. Additionally, LLVM-IR itself can be optimized, which allows for optimization passes to be shared between compilers for different languages as well. So LLVM is used by a variety of compilers, and it helps us to avoid all of this duplicated work. We've implemented a detailed semantics for the LLVM-IR in Rock that we call Vellum. And the goal is to be able to verify optimization passes, guaranteeing that they preserve the behavior of programs. And we want to verify compilers from languages to LLVM-IR as well. And for instance, we've actually already implemented a verified compiler from the Helix language to Vellum. So verification and formal semantics are great, but testing is still very relevant. For instance, we might want to have some assurance that our formal specification actually aligns with the real-world implementations of the LLVM-IR. And differential testing can help us by comparing the behaviors of programs in our semantics to real-world implementations. And this can point out any misalignments between the two. So LLVM is a big language, which makes it difficult to understand. For instance, this is the table of contents of the language specification, and it's actually really intimidating. So LLVM-IR has a fair number of complicated instructions, and this alone makes it difficult to tackle formally. But a lot of the complexity is also just like the result of interactions between the different instructions. We want to be able to justify optimization passes, and unfortunately, this results in complications to the language semantics as well. It may seem orthogonal, but optimizations often depend on the semantics. And in practice, there's a lot of subtle edge cases that we need to be able to cover in the semantics in order to justify certain optimizations. Memory is a particular instance of this, Low-level memory operations really disagree with optimizations. We have a whole paper on this that goes into a lot more detail, and I'd really love to nerd out about this with all of you later if you're interested. But for the purpose of this talk, the point is just that there's a lot of subtleties which make the semantics difficult to get right. And so the methodology for developing the semantic is really important. Okay, so LLVM is important. It's used by a bunch of compilers, but it's a complex language, and there's all of these subtle interactions of features that can lead to miscompilations. Building a formal specification of LLVM in ROC should help us understand all of these subtleties and provide us with a platform to verify the correctness of optimization passes and compilers. And that's what we hope to achieve with VELOM. So VELOM specification of the LLVM IR is structured similarly to a reference interpreter. We just take the informal specification of LLVM and convert it into a formal description of the language in ROC. To do this, we have an abstract syntax tree in ROC. So this is just a data structure representing the syntax of LLVM IR programs. And this is a good first step, but it's a bit of a lifeless description of the instructions used in the program. We breathe life into this by interpreting it into a mathematical specification of the language. And our first step in this process is to interpret it into something called an interaction tree. This is just effectively a graph-like data structure, which is used to represent the control flow of the program in a form that we can reason about in the proof assistant. And importantly, interaction trees also allow us to reason about non-terminating programs in the proof assistant as well. So interaction trees are built out of these visible event nodes, which are represented as different shapes in this diagram. The events roughly correspond to the different kinds of instructions in LLVM, and this allows us to implement handlers for different kinds of instructions in a modular fashion. Properties can be proven for specific handlers individually, and then we can lift those to the language as a whole. Some of the events are non-deterministic, like memory allocations, for instance, and handling these events leads to multiple possible behaviors, one for each choice for the non-deterministic. So the semantics of LLVM and ROC will ultimately have to produce a set which captures every possible execution that an LLVM IR program might have. This non-determinism is necessary to accurately model LLVM semantics, and it grants us additional flexibility for optimizations later on. So putting this all together, we get an end-to-end specification of an LLVM IR program. This specification is a set which defines all of the allowed behaviors of the program in the semantics, and the semantics is built out of this composition of interpreters for the different kinds of events in LLVM, which roughly corresponds to different kinds of instructions. And these small interpreters can be reasoned about individually, which simplifies proofs. We can also prove the behavioral equivalence of programs, like while ignoring the implementation of memory instructions, for instance, if it's not relevant to the proof that we're doing. An advantage of this interaction tree approach is that interaction trees are extractable, and this means that we can turn our specification into a verified executable interpreter relatively easily, and this enables our testing efforts that we'll discuss later. So VELOM currently supports a large subset of LLVM IR. If you compile a C program to LLVM IR, there's a good chance that we handle all of the instructions. We just might not have to handle some operating system library functions and stuff. It has a rich memory model, which should allow us to verify optimizations, even in the presence of troublesome operations like pointer to integer casts. We published this work in ICFP of 2024. And finally, we have this nice interpreter, which supports things like printf and command line arguments. And this enables our testing infrastructure, as well as our own testing generator, as well as things like CSmith and GovGen, which are existing generators. ROC has been invaluable for understanding the semantics of LLVM at a deep level. Formalization forces us to address many of the edge cases of the language. This is just a non-exhaustive list of some of the edge cases that have popped up when we've been developing the semantics. Some of these cases we were able to test for and find miscompilations in Clang. Some issues like address guessing are quite subtle, but they will impact our ability to formally justify optimization passes. Formal specifications ultimately demand clarifications, and they keep us honest. So we have this large semantics for LLVM and ROC, and now we can prove properties are bad of our LLVM IR programs. But there's still one big question that we'd like an answer to. How do we know that our semantics is the right one? Well, we can test this using our executable interpreter to validate our semantics using unit test and differential testing. Our formalization gives us this executable interpreter, and we can use this for differential testing by comparing the behavior of LLVM programs under our interpreter to existing implementations like Clang. If Clang and VELOM have different behaviors on the same program, then there's a bug in either Clang or Vellum. We wrote a tool to generate tens of thousands of random programs for differential testing. Our tool uses QuickCheck, which is a framework for randomly generating test cases in Rock. Generating LLVM syntax is straightforward, but LLVM is a complicated language and we need to satisfy a lot of constraints. So for instance, if we want to generate a division instruction, we might want to ensure that the denominator is non-zero. We might want to ensure that we produce valid pointers whenever we do a cast from an integer to a pointer. And for differential testing purposes, we need to keep track of which variables are deterministic so that we can keep the output of our programs deterministic as well, so that we can do a comparison of the results. We have a metadata system that allows us to track each of these properties, and so we can generate programs that use potentially dangerous operations safely. By generating LLVM IR, we've been able to find bugs in the Clang compiler. For instance, we were able to discover a bug with the extract value instruction. This instruction just extracts the last byte of this pack structure, and the value of the last byte is 0. And indeed, that's what the Vellum interpreter gives us as a result. But Clang has a very different notion of what 0 is. And this is because LLVM's implementation of extract value has an off by 1 error behind the scenes. One thing that's worth mentioning is that existing generators like CSmith and YorkGen wouldn't be able to find this bug because they produce C code. And the C front end actually is a bit biased and it avoids generating extract value instructions. Because we target LLVM IR directly, we can get a bit better coverage of the language as a result. So overall, we've had a good experience with the Rock Proof Assistant. We can define logical specifications of our programming language in order to provide strong guarantees about compilers and optimization passes. And we can combine this with differential testing in order to ensure that our specifications are actually meaningful and correspond to real world things. These takeaways, we hope, make Vellum a useful platform for formally understanding LLVM IR, its semantics and optimizations. This talk has been a broad overview of Vellum and its methodology, but there's a lot more to talk about. So it's really hard to work on a memory. So I've been really hard at work on the memory model, and there's actually lots of interesting questions about optimizations in low-level memory. You can see some of this work in this paper, and please talk to me about this. It's more interesting than you might think. Our friends at INRIA have been hard at work at extending Vellum with a concurrent and weak memory models. And of course, there's the verified Helix compiler that targets Vellum that we mentioned. We're currently looking into verifying more analysis and optimization passes, particularly those involving memory operations. And we're starting to look into the semantics of Rust through the lens of LLVM IR. So feel free to check out our project on GitHub and come talk to us throughout the conference. Thank you for your time.
Thank you very much. Questions?
Very nice talk and interesting work. I was wondering, can we use the LLVM to maybe compare the semantic of Rust against C for a certain implementation of an algorithm?
Yes, I feel like you might be involved in the tractor grant in some sense. Maybe not.
No, I
Okay.
I mean,
So actually, my advisor right now is not here today because they have to attend a meeting for the tractor grant, which is the translating C to Rust thing. Which
yeah,
we're going through.
I heard about that. I didn't know you were part of that because it was kind of secret, right? Until, no, that's cool.
Yeah.
Very
So
cool.
so the hope is that we can compare semantics by comparing the compilers on output.
Thank you.
Great talk. I have one question regarding the optimization path verification. Do you verify the optimization passes in the IR itself, or do you also verify the optimization that the backend compiler does? I mean, there was a path from the LLVM to backend compilers, right? So,
okay, so currently Vellum does not have a backend to any assembly language. It
Okay.
could in the future, and hopefully it will. But that hasn't been our focus. We've been primarily focused on the language semantics itself, which are surprisingly complicated. And past versions of Vellum have implemented optimization passes like the mem to reg pass, and we're hoping to revive that with the new memory model work that we've done.
okay, and for the intrinsics, which essentially ask the backend compiler to do some optimization, what kind of properties do you verify about the intrinsic itself?
About the intrinsics?
Yeah.
Oh, so the intrinsics in LLVM We kind of axiomatize them. So we provide, you can, and like users of Vellum can like add their own. You basically provide a rock function for those intrinsics, and like that's like the implementation, and then you can just like do proofs about it with the rock definition.
Okay, and there we assume like for that particular intrinsic, we assume that like we fix the backend compiler, and then we assume the backend compiler implements intrinsic in a way that axiomatize that in Vellum and do the proof. Is that the way to go forward?
Sorry, I didn't.
I can talk to you offline.
Okay,
Yeah,
sure.
about it. Thank you.
Okay, so that concludes our session. Thank you again, speaker. And let's take a break now. See you again at 3:30.
Okay, so I'm Alvin Goodlow. I'm your session chair for today. So we're going to get started on our last session. The first talk is by Max Bonnock. It's kind of it's a very deep talk. It's involves concepts we've seen across different domains of SAT, where you see it in complexity theory and you're reducing it to something else, and an informal method. So they're actually using a whole lot of ideas, including ideas from areas of math most of us don't work in. So we're going to have to like work together to ask good questions. The title is Strong Structural Bounds from MaxSat. And I will let Matt take it away.
Yeah, thank you very much for the introduction, and no worries. I know it's the last session, so I kept everything light. And also, first of all, apologize for being remote. I know this is always a bit annoying, so I hoped I could join you in person this year. It didn't work out. Maybe next year again. Let's hope. So this is joint work with Jay Grover, who is also here at ESA and the Advanced Concept team, and Markus Hescher, who was at MIT while we were working on this project. And yeah, the a bit buying subtitle of the talk is The Fine Details of Using Neuromorphic and Quantum Hardware Accelerators. So perhaps I should first start to explain what this has to do with MaxSat and the structural bounds and the reductions that were already mentioned. So in the last years, there were a lot of effort to build hardware accelerators based on non-standard computational paradigms. Perhaps the most famous one in the media is the quantum annealer that somehow claims to solve optimization problems a bit more efficient by using effects like quantum tunneling to escape local minima and stuff like that. But there are also other branches. For instance, neuromorphic hardware is getting a big hype in the last years as well, where you try to use spiky neural networks, for instance, to simulate computations more like as we expect in the brain. And this hardware has the promise to be very energy efficient and also radiation resistant. So that makes it very interesting for space. And I also have all of these things in common. Well, they have somehow the same interface, which is called the quadratic unconstrained binary optimization problem, or QUBO for short. So QUBO is a relatively classical optimization problem. You get as input a formula H with three variables x1 to xn. And then you have a lot of these quadratic terms, xi times xj times some weight w, which is usually a real value. And your goal is to find an assignment to these variables, to the booleans, such that this function is minimized. So this is a bit the computer science definition of the problem. If you look in the physics paper, then usually the variables are -1 and +1 or something like this. And the thing is called the ground state, but it's the same. And in a sense, all of this fancy hardware can be seen as a chip that solves this problem. So this is what we kind of have as a common ground. However, there are a lot of limitations still with this technology and a lot of problems that we have to face. First of all, and this is always very important to mention, these tools don't solve this problem exactly, so they don't give you actually the minimum and the optimal solution, but they give you a heuristic solution. And even worse, it's a bit hard to work with these things because you cannot inspect the solution over time. So you kind of in advance have to tell you how long you want to run it on the chip. But this is not a problem for today. So I will just assume that these are exact solvers. I will ignore this fact and basically we assume we have an oracle to QO. Everything we do also works if it's in the heuristic world, but this is not part of this work. The second problem that we face is, well, the U and QO states for unconstrained, so we don't have constraints. And frankly, this is very annoying and unintuitive. So we all used to work with constrained languages. And we like our constraints, and we cannot use it here. So that is a pity. And in order to then contain or encode problems to QOs, we have to deal with this penalty terms and all kinds of other strategies, which is very error prone. So people like to use instead another interface in front of the QO that is then kind of compiled down to QO. In theory, you are very open what to do. You can use constrained languages, you can use ILPs, but it turned out that maxset is a very practical or natural choice here. So maxset, the maximum satisfiability problem, I guess most of you will know it, is the following. You get this input Boolean formula phi in CNF with some weights on the clauses, which may be usually natural numbers or infinite. If it is infinite, we call it a hard cause or a hard constraint. Otherwise, it's soft. And the goal is to find an assignment that makes all of the hard constraints true and maximizes the sum of the soft constraints. So here's an example, a formula with two hard constraints here in the middle and for soft constraints. And for instance, if you consider the assignments that just sets everything to false, that's a valid solution. You satisfy the two hard constraints. You also satisfy these two things for value of 10 and 20. So overall, this assignment would have a value of 30. Or often in the literature, we also consider the inverse. So these two clauses we falsify. So we would say we will have a cost of 60. In this case, you can improve by quite a lot by just flipping the last bit. Then you lose this clause in the middle. You win the other two. So then you have a value of 80 and the cost only of 10. Okay, so that is a much more natural and well understood interface. And then there's a third problem, and that is that on the hardware, the QOs are not fully connected. So what does this mean? So if you consider this quadratic formula H that was defined in the QO, you can think about it as a graph by saying, okay, each of the variables is a node, and I put an edge between them if this weight Waj is non-zero. In the ideal world, you would like to choose all of your weights as ever you like, but by the design of the hardware, you cannot. So some of the values are forced to be zero. That is the topology of the chip. Maybe you have seen this graph here on the right. Sometimes in the media, there was the topology of the first D-Wave machine, but different vendors have different topologies. But what that means for us is if you want to solve the QO you have at hand, you somehow need to encode it into this topology. So you need to solve a graph embedding problem. And this is only efficiently possible and mostly only possible at all if your QO has low tree width. So what is tree width? Tree width is a tool from graph theory that measures the structure of a graph, or more precisely, it measures how close a graph is to being a tree. It's defined via the concept of a tree decomposition, which is the tree T, together with some mapping that maps the nodes of the tree to subsets of nodes of the original graph. So that is quite a tongue twister. So here's an example. So on the left side, we have a graph, and the right side is the tree decomposition. So it's a tree, and each of the nodes contains a subset of the original graph. And you need two properties. First, every vertex and every edge in your original graph must appear somewhere in the decomposition. And second, each node in your graph, if you fixate any of the nodes, then all of the bags containing these nodes need to be connected. And then we say the maximum size of any of these bags, that is what is called the tree width of the graph. So this is a measure of the structure of a graph. And you can lift this to a measure of the structure of formulas. by considering graphical representations of the formula. So for instance, the most classical one is called the primal graph. So if you have any formula phi, you define a graph that contains node for each of its variables and that connects two nodes by an edge if they appear in the same clause. So in other terms, each clause will be a click in the primal graph. And then the tree width of your formula is just the tree width of this primal graph. And second definition, you can change or alter this graphical representation. Another common one is the incidence graph. Here you also have a variable for each node for each variable in the formula, but you also have a node for each clause in the formula, and you connect the variable to the clause if the clause contains the variable. And then the tree width of this graph is called the incidence tree width of the formula. All right, so there was a lot of terms and terminology. So to wrap this part up, we have cool new toys to solve the QUBO, but to actually use them, we kind of need other QUBOs that have small tree width. And working with these is a bit annoying, so we rather would like to start with MaxSat. So the question is, how do we come from MaxSat to QUBO? And this is where this paper kicks in. And to think about it on the first side, actually, QUBO is a very strong relation to max2sat. So MaxSat with the property that each clause contains at most two literals. In fact, QUBO by definition is in a sense max2DNF. And then you can flip all of the terms to clauses, and then you have a max2sat formula. In fact, actually, it is monotone because in QUBO you don't have any negation. And it's relatively easy to see that in the maximization setting, you also don't need negation at all. You always can move your negation to the optimization function if you like. On the other hand, that you can reduce MaxSat to max2sat is well known since the 70s. So there's a well-known reduction. And this is in stark contrast to classical SAT, where, of course, 2sat is easy. In the optimization setting, it's not. But this reduction is in a sense only of theoretical interest, right? People showed this is a reduction, so max2sat is hard, and then it's done. But nobody really cared about developing a max2sat solver. We have MaxSat solvers, and that's it. But now the picture changed a bit because now we have these tools that can solve QUBO, and suddenly these reductions are interesting. But they are only really useful if all of these arcs preserve the tree width. So if any of these arcs, like the red one, increase the tree width of our encoding, then, well, we reach QUBO, but then we cannot use the new hardware. So we're kind of stuck at the last step. So we need to ensure that none of these encodings or transformations increase the tree width. And that is our main result. So this is the outcome of the study. We can show that given any weighted CNF and any corresponding tree decomposition, the following two things hold. First, MaxSat is equivalent to max2sat and to QUBO under linear time reductions and under reductions that increase the tree width by at most 2. So that means essentially you start with a MaxSat instance, and then you can rewrite it a bit. You reach max3sat, you can rewrite it a bit, and so on. And you can go this whole tour. You reach at QUBO, and this whole process, you increase the tree width by at most 2. And the second statement is the same is true for the incidence tree width. So all of these three problems are equivalent under linear time reductions that increase the incidence tree width by at most a factor of 3. So it's still bounded, but now it's much worse. So in the first case, we have additional 2, and here we have a factor of 3. Now in this picture, you may see some of the arcs are solid and some are dashed. A solid arc means that we don't need a tree decomposition for this encoding. So it's just a standard encoding as we like it. And implicitly, we can prove that it doesn't change the structure of the formula. Whereas if the line is dashed, then actually we need a tree decomposition as input to guide the encoding along this tree decomposition. Otherwise, we can not guarantee these bounds. All right, so this is the result. Now, how do you prove this? So how are these things working? And in a sense, I think it's very, very elegant at the end. We have a set of reduction rules, and all of these rules either are not applicable, then they don't nothing, or they are applicable and then they very slightly change the formula. For instance, rule 1 is just for demonstration purposes, a cleanup rule. So if there's a clause that has a weight W that is 0, then we just can delete the clause. And of course, if you can do this multiple times, at some point, all of your clauses are non-trivial. Great. And now we have a set of these rules, and for each rules we do 3 things. We prove that they can be implemented exhaustively in linear time, that they don't change the satisfiability or the value of the formula, and third and most important one, that they don't change tree width by too much. In this talk, I will only speak about the third part because I think the other two is more like the classical business, and that is the third part is what we care about. So to have a more concrete example here, rule number 2 is the standard rule that takes a maxer formula and basically shifts all of the weights from clauses to variables. So if you have a soft clause with some weight W, we introduce a new variable alpha, a unit clause that has just alpha in the weight, and we put the negated alpha to the rest of the clause and make it a hard constraint. So this is just a classical relaxation variable. Okay, and then we like to have lemmas like this one that say, okay, these 2 rules can be applied exhaustively in linear time, increase the primal tree width by at most 1, and in this case, they don't increase the incidence tree width at all. So how can we prove this kind of lemmas, especially how can we prove these statements about the structural properties of the formula? So what is the reasoning? And the reasoning here and always in the following rules will be, okay, before we apply this rule, we will have a formula, and this formula has an optimal tree decomposition. Assume we know it. It's this one shown here. Of course, it's just a snippet, so we'll extend to the top and to the bottom of the screen further. What do we know about the tree decomposition? Well, since this C is a clause, it is a click in the primal graph, and hence there must be a bag containing all of the variables appearing in this clause. Maybe some more, but at least these, they must be in. So now our reasoning will be, when we apply the rule, we would like to implicitly also modify the tree decomposition so that we have a valid tree decomposition for the new graph, proving that the tree width didn't increase. In this case, it's very simple. We just attach to this guy a new bag with the same content plus alpha. Then it's easy to see that this is 1 larger than this, so tree width goes up by 1. And it's still a valid tree decomposition, so all of these variables here are also here, so it's still connected. Alpha just appears here, and these 2 new clauses are happily satisfied by this new bag. Also importantly, if we apply the rule again, we will not apply it to this clause, because this now is a hard clause. The input to the rule was a soft clause, so we will never touch this increased bag again, and so it can never happen that we increase the tree width by more than 1. All right. So that was a simple example. Let's get a bit more fancy. Now we are maxed a bit cleaned up, and we actually would like to go to max free sat. And this rule is basically your textbook reduction from sat to free sat. Nothing surprising happening. So you have a clause with q larger than 3 literals. You introduce a variable and you get 2 new clauses, one with L1 and 2 and alpha, and then one with not alpha and the rest. And indeed, this rule also increases the primal tree width by at most 1. And the argument is basically almost the same. So before you apply the rule, you think of your tree decomposition. There must be a bag containing this clause. To this bag, you attach a new one with alpha that already makes these 2 clauses happy. But now we need to be careful because this clause is a hard clause, but the original clause was also hard. So now if we apply the rule again, we could maybe pump up this bag even further. But we can avoid this by actually adding 2 more bags to this one, one for each of the clauses. And then you can see that this clause, this bag corresponding to this clause is actually smaller than the original bag. So if we now apply the rule again, nothing can harm us. In practice, by the way, often this rule decreases the primal tree width. So imagine you have a very large clause and you split it into 2, then actually you add structure to the formula, so the tree width can also drop, but it increases by at most 1. Now, in contrast to the lemma that we saw before, note that here we don't have any statement about incidence tree width, and that is the case because this rule is very unclear what it does to the incidence tree width. The reason is in the primal graph, all of these variables appearing in the clause are nicely stacked locally somewhere in the decomposition. But in the incidence graph, they may be spread across the whole decomposition, and randomly splitting this clause may actually increase the incidence tree width by quite a lot. So therefore, we need a different lemma here, and this lemma takes as input the formula, but also a tree decomposition. Remember, this is the dashed line in our picture. And here we can do a thing, something that I think is a very neat trick. So if you ever heard about tree decompositions, they're very famous to run dynamic programs in them. And actually, we can use the insights of these dynamic programs and simulate them directly in our encoding. So to get from max set to max free set, we can write basically a dynamic program within the formula that simulates the original formula. And this is surprisingly simple. So just for every clause in our original formula, C, and for every node in the decomposition, T, that contains this clause, we introduce a variable CT. And basically the semantic of CT is clause C was proven to be true at node T or below in the decomposition. Now, this first clause here, this root TC, that should mean the top point in the decomposition, so the highest node in the tree decomposition that still contains the clause. And if in this point we satisfy the clause, then we get whatever the weight was of this thing. So this is this gives us the value. But of course, we cannot just randomly set a clause to true. So we cannot just set any of the CTs to true and are happy. So there need to be a reason, there need to be a certificate of why we can do this. And this is basically the dynamic programming step. So if we set the CT to true, then either of the following must be the case. Either in the back T, we prove that C is correct, is satisfied by having a literal in this back that is true, or we did it before. So either there is a child of T prime, and in this T prime, we proved that C is true. And then actually that's it. We can forget about all of the original clauses and we are happy. Well, now you may say, wait a minute. You said you want to go from max set to max free set, and this thing really doesn't look like a free set formula. And here we can do a nice trick from graph theory. So there's a theorem for tree decompositions that tell you can morph any tree decomposition such that each back has one of two types. Either it has exactly two children and they have the same content as you. So in this case, you have one variable here. This is 0 and then 2 here. So 1, 2, 3. It's a free clause. Or you have exactly one child and it has exactly one literally less than you. So in this case, you have 1, 2, 3, and it's also a free clause. So you can kind of repair this encoding purely on the side of graph theory. All right. So then we are at max free set. We have to go to max 2 set. These rules are a bit boring. So I just skim over them. The left one is the rule that basically gets rid of hard constraints by adding penalty constraints or top values. So you sum up all of your soft constraints and you replace hard constraint by this large number. That of course doesn't change the structure. And the rule on the right side, that is the one that replaces free clauses with free literals by binary clauses. And that's the usual trick. So you replace a clause by a set of clauses, 6 to be fair. And this set of clauses is not satisfiable. But if you satisfy C, then you will satisfy more of these clauses than if you not satisfy C. And then in your objective function, you will see whether or not you satisfied your clauses. Okay, so and these two rules can also be applied in linear time, and they will increase the primal tree width by at most 1 and the incidence tree width by at most a factor of 3. And then maybe the last two rules, and one that we can also study a bit more, is rule 6. So now we want to go from max 2 set to monotone max set. So monotone for us means everything is negated. So it's a bit counterintuitive. So what we have to do is if we have a binary clause, which has a positive variable x and some other literal L, we want to replace this x by something negative. And to do that, we introduce a new variable alpha, with the semantic not alpha is the same as x. So this clause should be the same as this. And then we have to encode, well, then alpha is the same as non x, which is done by these three clauses. Now, this rule is interesting because it increases both the primal and the incidence tree width by at most 1. So the case for the primal tree width, I could let you do the proof now because we saw it already 3 times. So you start with your decomposition. Somewhere in the decomposition is X and L, and you attach a few new bags to it, and you see, okay, the primal tree width doesn't grow. But how does the proof look like for the incidence tree width? This is much more complicated because in the incidence tree decomposition, world looks a bit different. So remember here, we also have the clauses in the decomposition. So the C is also here. And all we know is that C and X needs to be in one bag and that C and L need to be in one bag. There's no guarantee that X and L are in the bag. And we actually doesn't know anything more. The only thing by the definition of a tree decomposition that we know is that on the unique path between these two bags, we always have C in the bags. So what we can do is, since we delete this clause, we can replace in the tree decomposition every occurrence of C by our new introduced variable alpha. So we get something like this. And then we have a lot of points where we can attach new bags to that cover all of these new clauses. So for instance, this clause not alpha or not X, we can put here. So we have a new bag containing alpha, X, and this clause. And we can do this for all. And then as before, the only thing where we can reapply the rule is actually this clause. So here we can add some more auxiliary bags to make sure we can apply the rule again. And just from the picture you see for the incidence graph, everything is a bit more complicated than for primal tree width. Okay, so now everything is monotone. So all our clauses have the following form. And then actually we already have a cubo, which is flip everything. And then we have a cubo. All right, so this is a bit how we do it. I have 2 open problems for you. So on the primal tree width side, we are very happy. So everything is equivalent under linear time reductions, and it gives us a +2. I think that's pretty much optimal. For the incidence tree, with a lot of questions are open. So here we give you the tree decomposition, you have it as input, but you also are worse in the sense that we have the multiplicative factor. So the first question is, can we reduce from maxsat to max2sat by increasing the tree width only by an additive factor instead of a multiplicative factor if you are given the tree decomposition? And maybe you can already also run in polynomial time, doesn't need to be linear time. On the other hand, if I take the tree decomposition away from you, so can you still do it? So with the tree decomposition, we have kind of this bound. And the question would be, can you have the same bound without actually using the decomposition? Because this is, of course, in an encoding, not the nicest thing to have to request the decomposition. Okay, so to summarize, maxsat is a nice interface to QBOS, and we can do the whole reduction structurally preserving. So this means these 2 problems are not only equivalent under polynomial time reductions, but they're actually equivalent under much stronger reductions that keep the structure in place. If you find this project interesting, please have a look at the QR code in the middle of the screen. It gives you the project site. If you have any cool ideas or would like to work with us, then scan the QR code on the right. And with this, thank you very much. And yeah, if there are any questions, I'm still a bit here, I guess.
Yep. Any questions? So I kind of have a question, but so you've started this process that leads you from sort of max set all the way to around the diagram here to chasing arrows like category theory, which is, you know.
Yeah.
I do try to get a cool category theory joke in whenever possible, which, you know, I see some smiles out there. So the end goal is that we get the QBOS so we can apply it in these cool new architectures. You know, how far of a leap do we kind of go to kind of get a diagram down where we can, you know, run stuff on these new architectures? Because I know this is kind of like a long step to get there.
Yeah, so so the problem of actually so the reductions, we test them in the sense that they were very nicely, and if you use like other traditional tools to solve the QUBO, then that makes all sense. To actually use these hardware tools, they are all, I don't know. So as far as I understand, very in early stages still, depending on whatever they say. So you have two problems. So they are by design always of fixed size. So, okay, they can solve maybe a QUBO with, I don't know, 200 variables. So also auxiliary variables will hurt us, stuff like that. Here tree width helps as well, because if you have a low tree with QUBO, you can split it nicely and then maybe solve it in parallel. How much of an so I would say that maybe to get back to the question, so the quality of the chips is so that it can solve instances of a size that we could solve anyways currently. So that is a bit, if that is the question. So they need to scale up so that the whole thing will be useful. I think, though, our experimental part to the paper is still also in progress.
Yeah, I knew kind of all of this stuff is still in like, pre-beta testing phases, so we say, but it looks like you're trying to be ready when these machines become practical. So any other questions? Yes, Aaron, he's got probably a deep mathematical question.
Oh gosh.
So the question I have is, so to go from MaxSat to QUBO, essentially you have to take, I guess if you're doing incidence tree width, you have to take one of the dashed lines.
Exactly.
And that means that you need a tree decomposition to get there, right?
Yes.
Is it true that you need a good tree decomposition to implement these things in QUBO anyway?
So the dashed line means so the solid line means the original tree width of the formula, the best possible, is increased by at most 2. The dashed line means if you give me any tree decomposition of width k, I will output a formula of tree width at most 2k. So the better the decomposition you give me, the better the dashed line is.
Okay.
And this is why also, sorry.
Sorry. Just my main question was to actually implement one of these problems on a QUBO chip. Do you need an efficient tree width decomposition, like to program it onto one of the chips?
Yeah, so you need an algorithm that gives you a tree decomposition, but it doesn't need to be the optimal one. So if you have a good heuristic, and we have good heuristics that very quickly give you a tree decomposition, it's not the optimal one, but it's close to, and then this all still goes through.
Okay. Perfect, thank you.
So that being said, we implemented it.
Okay, well, let's thank the speaker.
Thank you very much again for having me.
Okay. Okay, our next speaker is Benjamin Valpy. He is going to talk about the formalization of mixed precision matrix multiplication using sort of SMT lib type language. So take it away.
Hello, everybody. Yeah, thanks for the introduction. My name is Benjamin Valpy. I'm a student at the University of Rochester, a PhD student at the University of Rochester. And yeah, I'm going to get right into it. I'm going to start with just an introduction motivation to why this problem is necessary before I get into why I think SMT is a good choice for hardware simplification language. Or, well, not hardware, but like for what we're trying to accomplish here. We're going to talk about the nitty-gritty details with that gets into the numerical behavior of tensor cores. But fortunately for me, some other earlier sessions have talked about floating point nuances, so maybe you'll have some primer there. There's many people doing that. And then finally, we're going to end with kind of showing off what we can do with a model. Okay, so it's not hardware complex, so this might not resonate with all of you, but today's practices are increasingly complex. Users also require suitable documentation to utilize them correctly and effectively. Now, when it comes to GPUs, which is spoiler alert, where tensor cores are put in, the device are put into, the documentation for these devices is scarce and insufficient. For instance, NVIDIA, the big graphics card guys, their hardware implementation is often hidden behind these software libraries that simply expose the functionality of the unit, and they don't really tell you what is going on underneath. So in many cases, particularly here with tensor cores, even these software libraries are just insufficiently documented. And so that presents a challenge, which is how can we replicate the behaviors of these undocumented hardware units and reason about that? So right now, what interested folks do is they'll resort to manual tests and experiments in order to build and understand it. This can work in small segments, but as an academic community, it kind of ends up we're in this fragmented and sometimes even contradictory knowledge, right? People have found different things. They're not really communicating with one another, and that's not what we want. So how do we address this challenge? Our solution is to ideally have hardware vendors, but in lack of that, folks like hardware computing students like me specify a model that can then be evaluated against hardware. So there are the next couple of questions that goes with this is what choice of language, like what are we going to use to specify the model, right? There are a couple of different formats that can be used. All right, sorry about that, folks. That's spoiling. Okay, so let me correct myself. Right, so what we're doing right here to answer the question is we want to choose an appropriate language or way to communicate the specification of these units, right? If I'm here criticizing the existing documentation, I want to make sure that whatever I'm presenting with doesn't have similar faults, right? So the first thing that we might ask is English, right? So United States specs, maybe you have, maybe you haven't. That's one choice. And I've included a snippet of a real ISA spec from NVIDIA. And one of the benefits of English is that it's really easy to communicate. It's easy to read about properties that are presented in there. But remember, we don't want to do a lot of work because we have not so much time on our hands, and we have additional steps we have to do if we want to evaluate that specification of hardware. But then the next choice you might think of is a language like a pseudocode or maybe just exactly C language, just specify semantics. But this has other problems. While it's really easy, operate against hardware, you just run that C program and check what it does. It's a lot more difficult to reason about the property. And in this particular case, which is why I chose it, if you're the aficionado, you might understand that, well, he has undefined behavior if the value of B is greater than the width of the left operator, right? So is that coming into play here? And there's all these questions that arise. Now, we opted for SMT-lib as a specification language. And I'm going to tell you why. Why? Well, actually, no, I'm not going to tell you why. I have to put that out. I'm going to say that it's because it avoids both of these, and the specification language is very precise. It doesn't have all these folds. There's not undefined behavior in it. It easily reason about it and execute it because they're evaluators for SMT-lib. Let's go through an example of how we would use SMT-lib to accomplish our goal of documenting an unknown operation on the hardware, right? So let's start with something simple, unsigned addition. So our first step is to build a formal model, or like a starting point for formal model, right? You have some intuition about what the instruction does. Disclaimer, you do need some domain knowledge about the operation of that the unit is performing in order to start, right? If this is completely black box, this particular mechanism of reverse engineering does not work. All right, so we'll start here with this starting model, and we list some property of interest that we're interested in evaluating again. So unsigned addition, we just want to know the addition overflow, right? The next step is to formulate this property as an SMT query, which in SMT lib you just throw it down, and then we obtain a witness or an example, some set of values that we can use to test this property, right? We then provide those values to hardware, which will then tell us what the actual unit is doing, allowing us to then update our model with the behavior, right? So in this case, maybe we found that when we tried to add 1 to the integer max, it stayed at integer max, and so it wasn't overflowing, it was being saturated. And so with that, we then have, we can continue that for more of the properties and repeat, but that is the gist of what's going to happen here. Now we get to something way more complicated than unsigned addition, tensor cores. So what is a tensor core? These are specialized units designed solely for the purpose of accelerating matrix multiplication in AI, well, in these graphics cards, and they're a thing because of how prominent AI is, right? So what it does is it just computes this equation up here. Specifically though, at least for the earlier generation units, A and B are always half precision input, which is floating point 16, whereas the C and D matrices, your accumulator matrix and your resulting matrix, may be half or single precision. Now this leads to a couple of questions, especially if you're like a floating point guru, right? There are so many unanswered questions here. Well, what's the precision of intermediate product and sum? What rounding mode is used? Is there an order to the accumulation, right? When you're doing the accumulation order, accumulation floating point numbers is generally non-associative. Yeah, so you have all those questions, and then the next question is like, what for exceptional values, for NANDs, for subnormal. Without an answer to these questions, it's quite challenging to create software or hardware that can match the tensor core behavior, which is a particularly pain point for those that are trying to port algorithms that might be written for CPU to GPU. You want to know how these results might differ, especially if the algorithm you're writing is very sensitive to these nuances. So I'm not new to this game. There has been prior work that has studied the numerical behavior of the unit, but generally using a test-based strategy, and that wasn't quite good enough for us. But we have a starting point here. So for instance, Hickman and Bradford in 2019 studied these cores, mostly focusing on the analysis of the error bounds, which we're not as interested in here, but also did some exploration to how they handle the exceptional value, which is in infinities. Much more relevant to our work is that of Fossey et al. In 2021, where they did explore the questions of the numerical properties that I showed in the earlier slide. They found a couple of things, but quite interestingly, I want to point out one that is most interesting is that these partial sums are not normalized. I don't have enough time to tell you exactly what normalization is, but you can look it up if you're curious, and you can find that that's quite an interesting observation that they found in these units and properties. They also did a couple other things, like showing that the accumulator uses 2 extra bits for carries, and determined that additions are performed in single precision with round to 0, right? Remember that the inputs are half precision, so what's the format that we're using for intermediate addition? However, in our work, we actually found that these were not quite accurate. I'm going to get into those. Also, of course, there are actually other works. I just want to put that as a disclaimer. These are not the only two that's behavior. Okay, cool. So, with going through the process that I explained in the earlier slides, how are we going to apply this tensor cores? Well, we're just going to generate witness inputs automatically from SMT for each of the properties that we're interested in. Now, remember, expressing these properties does require domain knowledge of operation these units are performing. So you have to have an understanding, or have someone with an understanding of the different ways that, in this case, matrix multiplication might be implemented in hardware, so you know which properties to have. And that is one downside of this method. So, but what we can do then is use our method for each property of interest. So as long as you can formalize it and the formalization is tractable with the SMT solvers that we have, you can create a witness that you can then use to evaluate the hardware to get the property, to get a model of that property, how that will behave. And so, as I mentioned just in the last slide, we use this process for all of the properties that we can think of, and all the ones that Fossey did. And we did identify 2 issues. So the first, and the one that we're going to talk about here, is that tensor cores don't actually use round to 0. They actually use
very similar to around to 0, but is subtly different. We also have this other observation that tensor cores actually require 3 carryout bits due to lack of normalization. Yeah, that's one note, but we'll get there. And then we use this method to across multiple generations of tensor cores, which so volta, turning an ampere, and each generation has subtle differences in their implementation that influence their numerical behavior. Okay, so visualization, right? Just building a formal model. We're focusing on one dot product step for multiplying the first row of A by the first column of B, adding it with the first cell in C to get the first cell in D as a result. This gives us, the equation below. That isn't important here, but just to have a visual to work with as we're going through these slides. So remember, tensor cores multiply matrices that store half precision values, but may accumulate with a matrix that may be either half or single precision. Remember how I said that documentation from NVIDIA is not that specific? That is a quote that tells you basically as much information as you get from them about how these things work, which is that the FP16 multiplier results in a full precision product. Okay, let's take them at their word for that and examine how we would use our method to verify that claim. So we pose our first property is multiplication performed with half or single precision. So this is how we would do it in SMT. This is kind of a visualization, but the first step is to encode the different possibilities. But in particular, and this is very vital, that you have to make sure that you are fixing what you're trying to test to just that being tested. So here you have to make sure you're heeding the other factors that may influence the result, so that you know the property that you're testing is isolated to just that property. So in this case, we're making sure that the result that we're comparing against is agnostic of the rounding mode used during the accumulation step, during the the multiplication step of the half percent. And then we just evaluate this. We use an RST solver to give us some values, provide those values to the hardware and see what the behavior is. When we do this, these numbers aren't important, but what we find out though is that the hardware result, it is actually what NVIDIA says, and they are indeed performing multiplication in single precision, at least not half. The next property that we want to examine, which is the one that we kind of discrepancy between our working posses, is which is the rounding mode that is used during the accumulation step, right? So you multiply all the values in A and B, and you're going to sum them, accumulate them together. What are the rounding mode that is used during that step? So we use SMT here to obtain inputs which discriminate between each pair of rounding modes. That's another slight downside is we have to do these properties in a way that is just testing one thing at a time. So if you have multiple possibilities, you have to kind of pit them against each other to get a counter between the two. So first up, numbers again aren't important here. I just want you to look at the highlighted portion. Here we find our first test and we show that the hardware agrees, and it says, okay, it's between RTP and RNE. It agrees with RNE. Between RNE and RTZ, it actually agrees with RNE. So already we've found an issue against FOSSI, what they concluded. Here we're checking RNE and RTZ. We have multiple inputs because we're testing effective subtraction and effective addition. And so we have another one, and it's like, oh wait, in that case, it's not actually even RNE. Okay, so let's keep going. I think this is where it kind of gets blocked. Sorry, folks that are at home. But this one says not RTN, so it's not RTN, it's RNE when you compare the two there. And then when we do our last comparison between RTN and RTZ, we find that it is still RTZ. This is confusing, right? What's going on? These are basically all the rounding modes that we have in IEEE 754. And so what's happening here? Well, kind of a very small technicality here. RTZ, IEEE 754 says that the result is the format's floating point number closest to and no greater in magnitude than the infinitely precise result. Generally, how you would implement this, you would use a guard digit. FOSSI et al. Correctly concluded that there are no guard digits used. Let's think of a case where this comes into play. So you're having 2 power 1 minus 2 power negative 24, shooting this in single position. During the significant alignment step, which is where you make those exponents the same and you shift them in chases, all of the bits from the 2 power negative 24 term are lost or shifted out, depending on when you applied the negation of the subtraction, right? But in this case, they're all lost, they're shifted out. And so generally you would have a guard digit to keep this information. You don't on the tensor cores. And so when the actual result in RTZ according to IEEE 754 should be 2 power 1 minus 2 power negative 23, the actual result on tensor cores is 2 power 1. But this is not round to 0, and it's not any of the other rounding modes. And so we didn't know what to call this. I'm not great at naming. So I just said, oh, okay, let's just say they perform truncated rounding. Yeah, they're just truncating all of the bits. So during the significant alignment step, any bit that is being shifted is just dropped. Okay, not you. We also did the next property that we wanted to examine here is that Fossey showed that it's a little confusing. They came up with this formula to show the number of bits that you need when you're not normalizing to handle the the overflow. And they did get this correct formula, which is you need the ceiling of the log base 2 of the number of terms being added. But then in their conclusion state that they only need 2 terms. Or sorry, 2 extra bits, which is not the output of that formula. And I don't think this is that they got it wrong. I think that if they were doing manual testing, the finding inputs that could prove that you need 3 bits was a little more challenging. Fortunately for us, we have SOT solvers to back us up, and they were able to answer this question. Okay. They were able to answer this question quite easily, right? It's a great task for solvers. And we found some inputs, and we show that can prove that you do indeed need 3 carry-out bits. And the numbers are they're not nice, they're hard to read, but if you plug these into the hardware, you will find that yes, indeed, if you don't have 3 bits, you cannot get the proper result, and the hardware is using the proper result. We can also prove that no more than 3 bits are needed. If you assert the resultant difference between 3 and 4 bits, you also get on that. You know that hey, you have some assurances that you don't need more. So this is a summary of all of the properties that we studied in the paper. I don't have obviously enough time to go through all of them. We can find a discussion of them in the full paper if you're so interested. Great. So what's next? We want to analyze. We want to use our model, right? Our model is great and all, but what can we use it for? So the benefit of using FFT as a language here is that at the end, you actually have a model that you can easily use for running some analysis on algorithms or whatever, what have you, that will use these units. And so what we did was we focused on implementation of what they're doing here is okay, so let me restart. So tensor cores are these really cool units that do matrix multiplication really quickly, but they do it quickly because they're limiting the precision that they're doing the multiplication at. So some very, very clever algorithm designers wanted to figure out if they could use tensor cores to do single precision multiplication, which sounds incredible, but given that tensor cores are doing half precision multiplication. But basically, they use these clever strategies to basically use half precision and store the difference in the residual matrix. You can see the exact formula up there on the slides. So Markades et al. Is the early method that they first come with this method that they would store the lost main bits in a residual matrix, and then the error correction technique to fix the values of the loss, right? And then Otomo and Yokota, they come up with this method, and they noticed that the methodology that was done in Markades et al. Was it was great and it's fast, but it had some issues with error. And so they were like, what is the best way to, or what is the likeliest cause of this error, and can you refine it without sacrificing performance? They noted, likely by reading Fossey's work, that these tensor cores, their rounding is the source of the error, right? Because tensor cores are doing round to 0. They're really doing truncation, but not meaningfully different from round to 0 unless you're doing subtraction, so it's close enough. And they argued that the lack of using round to nearest is the primary source of error. And they were, for the most part, correct. What they did was they made the algorithm. They used tensor cores to do the multiplication step and the accumulation in just the matrices in the tensor cores, but accumulating into the final resulting matrix they would do outside the tensor core, which would mean that you could not have to be subject to the round to nearest, and you could use not subject to round to 0, and you could use round to nearest. Great. But of course, you're doing stuff outside the tensor core, so you're losing some performance. The question that we asked is, well, if you're sacrificing some performance, does that mean you're guaranteed more accuracy? Right? That's a good question. So our initial thought was, yeah, of course, right? You have round to nearest here, and so what would happen? So we use our model and with part of FFT solver to actually evaluate this. And to our surprise, honestly, when I wrote this, I was expecting it to just say, yeah, it's always better. It actually is not. There are a space of inputs where the method that is done by Otomo and Yokota is actually have a result that it has more error than that of the method that Norcadia. And the reason for that is fascinating. The reason actually has to do with the fact that tensor cores do not normalize their intermediate results. What this means is that while you're accumulating these numbers together, right? So you have 5 numbers and you're doing A and B, and then that results to C. If you're doing it outside of a tensor core, you're going to normalize in between each pair of addition, and you're going to lose some bits that could be carried up. By not doing this, lack of normalization actually preserves information that would have been lost during the significant alignment, right? And that is why in these, with these small spaced inputs, you'll see there's the result of their algorithm can be worse. Now, this is not a knock on autonomous method. It is very sparse phase of input where this error actually comes into play. So it is true, their claims in their paper, they did all these experiments showing that their algorithm is generally still more accurate than Marquis et al. It's just not always better. And so with that, I want to point out here that knowing the numerical behavior of hardware is vitally important. It allows us to design better algorithms. Otomo and Yokota were only presumably able to improve upon the original method of Marquis based on the knowledge that tensor cores were using round to 0 as their rounding mode. If they didn't know this, they would not have, they would have been more difficult to identify a way to improve the error by switching to having accumulations in value. And also, as a plug that I probably don't need to convince this community of, we can use SMT to create a full specification for hardware. And this is great. It allows us to easily compare our model to hardware and reason about its behavior. So with that,
Yep. Question. Okay. Here.
Thank you. It was a great talk. I have a question. I mean, I'm having a hard time understanding what SMT model you're referring to. So when you say SMT model, do you mean like, so whatever experiments you have done here with the tensor cores, trying to understand the rounding mode and stuff, are you trying to mechanize those results into SMT? You know, for example, like SMT-lib has the float space, like for binary 64 and 32, they have well-defined semantics in SMT-lib. Are you also trying to do something like that for FP16 or some other floats or something like that?
That's a good question. So what we're actually doing is the SMT model that we have is essentially an implementation of the operations that a tensor core is doing in SMT. So you just have a model you can evaluate that has the exact same behavior. Well, hopefully, if we've done our job right, has the exact same behavior as what the actual unit is doing. And so you can use that model in experiments. You can, like we just spoke on the photo, we can see if you, use SMT and whatever theorems you have, and have, when you would invoke that a tensor core and that operation, you use that in proof. So we use SMT for 2 things. One, to actually have an executable version of the tensor core that we evaluate on, but also we use SMT when we're identifying the properties of the unit. So to say, okay, what's the rounding mode? And so we have it generate witness for us. That answer the question?
So my question is, it's much more generic. So I'm just trying to understand where this leads to, because let's take a very concrete example of numerical linear algebra, right? So let's say I'm doing eigenvector, eigenvalue decomposition, right? So any numerical linear algorithm typically will require backward error analysis, which I'm sure we'll come into, right? Because it's not just one step. So let's say we are using SMT to verify its XP operation, A equals B into C plus D, right? And it's true due to the fact that, NVIDIA, not even, I don't think it's a new problem. That's why they came up with 7x4, because you don't know exactly how much the rounding error is going to cause difficulty later on. So the goal of this research is to let NVIDIA know, please publish what you're doing. Are you using 16-bit or 32-bit? But even if you do that, it doesn't obviate the need for backward error analysis for numerical linear algebra, because it's a lot more difficult problem, because you have to do it. But if you are saying, if NVIDIA publishes their exact spec, I don't need to do backward error analysis.
Oh, no,
No,
certainly,
right? Yeah.
certainly not arguing that. No, no, no. If you had the spec, I would believe that it would be easier to do backward error analysis because you have a starting point. You kind of have an inkling for where, like where to start. Like you have some model, and that's actually kind of where we're taking the work. So, we're using what we're doing error analysis kind of recorders in our current project that's based on what we do. But yeah, by no means can you avoid that. But yes, to answer your first question, yes, we would love for NVIDIA to publish a semantic, although that would mean I have left up to talk about it.
So following up on that question regarding the backward analysis, like can we use the SMT model that you have for now, that you have here to do such kind of analysis? For example, like now that tensor code uses this kind of has this kind of run behavior and a particular way of accumulating errors, can we do a backward analysis on the algorithms, like linear algebra algorithms using the SMT models that you have? Or is there still some work that needs to be done to do this kind of analysis?
I think I missed your question.
So my question was like using the SMT model that you have here, can we do backward error analysis for the linear algebra routines? Or is there something else that needs to be added to your model to do such kind of analysis? Because doing such, we need like well-defined semantics for like say, addition, multiplication, and stuff, right? So
I think the limiting factor that was you would actually be using SMT to do the error analysis. I think you'd rather have an implementation that's a little bit more optimized for performance computations. Perhaps I'm understanding your question, but otherwise, I think you have the ability to execute an arbitrary value, so that's different than our model. So does that answer? I'm sorry.
I can follow up offline.
Okay, yeah, let's do that. Yeah.
Yeah, I just have to comment that this kind of reminds me of the work that they have been doing on modeling memory models, where the vendors have, in our new multi-core world, have kind of hidden and simply refused to tell us how these memory models really work. And the GPU people are like this too. Well, we aren't going to tell you. We'll just give you a half a shadow of a picture, and there are consequences to that shouldn't be acceptable, but we have no choice. So fortunately, people like you are doing this, and people like Peter Sewell and Jade Alglave are doing this. But they're doing one thing I know Peter and Jade have done is they built domain-specific languages. After having spent time doing this kind of level modeling, they kind of took that experience to another level. And I was thinking, when he was asking the question about the backwards error analysis, I'm kind of wondering if you could build maybe an EDSL or tool for incorporating this as part of it to kind of do those types of further analysis using your model.
The answer is yes. Spoiler, and my other work is actually reverse engineering the entirety of the semantics for every single instruction in the SAS language. And I've done we're working on doing precisely that. So yes, thank you. That's I love it. Yeah.
Okay. Thanks. Let's give them a round of applause for great work. A laser pointer, is it? Yeah. So our final talk of the day is from a team at GE. Sarah Bernazzi, am I mangling it too badly? Will explain, give us a description of trace, a toolkit for requirements analysis, capture and elicitation.
Hi everyone. Yeah, it's a pleasure to present at understand. So Alvin mentioned, so language is domain-specific language for requirements engineering is Trace, toolkit for requirements analysis, capture, and illustration. So we have quite a strong team, formal methods for this basically called knowledge discovery and hierarchy of the research. And there were some power electronics engineers also part of this project. So as I go into details in big here, so why this domain-specific language, where does it fit in, is this. So we have this context of systems engineering where we are trying to apply. You have these requirements in natural language in a typical engineering project, and you want to weed out inconsistencies in them. Right? So well understood problem, and we translate these natural language requirements into a problem. That formalism could EL, SMT encoding, whatnot, and post that formalization and analysis, there are some downstream obligations also from a certificate system standpoint. So this is a bit of an advertisement of some of the tools that we've been developing on some program. So the novelty, if you ask the novelty about Trace, it's really in the multi-domain aspect of it, which I'll go into. So Trace, this is like the feature summary of it. So when we are modeling these requirements, then typically when engineers, they have a certain model of a system, and that's what we call as a system description. So we describe the system in terms of components, subcomponents, subsystems, what's their support for data types. Are they having any data types in mind? Are they referring to any units in the description of the system properties or variables? And also we have these subtyping. Pretty much when we want to describe types of systems, subcomponents, and so on, subtyping has become essential. And then there are these low-level requirements, and so examples of what are low-level requirements. And there are few high-level requirements also that could potentially decompose these low level. Again, these will be fewer from examples. Essentially, we are constraining behaviors or variable ranges of a system and what are the domains involved in the in the constraints of these variables. And going with the language, we also have these IDE, which is kind of implemented the whole thing. And at that time, I'll go into a couple of demos. Okay, so this is Trace by example. Okay, thanks. So type declaration. So this is somewhat like a controlled natural language, if you will. So here is like a power conversion controller translating. You're declaring a component type with some variables. You're declaring type. Packaging code. This is pretty familiar, and this is units. And when you want to describe these sorts of engineering system, units become pretty important. And you can note that this is like start of an identifier. We don't do sophisticated dimensional analysis, but there's some sort of unit checking that's going on. And so here are the specifications of units. So this is like your building blocks of system descriptions. Well, subtyping is, so you have a power conversion controller. Now there are DC controllers, DC controllers, and they could have variables of their own. And they support for enumeration because you need to capture variable values in a more meaningful sense. And these enums become pretty important. And we also have support for record types, but in our example, we haven't used it so much. And this is the novel aspect where we introduce this concept of domain, where you could have power electronics domain, you can have thermal domain, where you could specify sorts of equations associated with that physical domain. So here are these requirement types. So these are like unconditional statements. System shall set value of a variable. And people who've seen requirements languages, it's very familiar. So this states some unconditional features of a system. The condition action requirements are system shall set a control variable, a variable that the system is going to modify, while when it's monitoring the state of a variable and it observes a condition that is greater than a certain value. So these are typically what we call it low-level requirements. And here are these high-level requirements where they're stating some high-level property. The aircraft can provide a certain amount of power. The battery shall weigh certain kilograms. And also equations. Equations are essentially calculations, but engineers like equations. So they want to capture information about their system in these equations. This is like simple power calculation. And you can see that we have units associated with it. Multi-domain requirements are here. We're sort of structuring these requirements as per the domain of interest. So battery domain is going to have your battery power obligation for your system. Power electronics domain, you can capture the power converter efficiencies, the losses associated with power conversion, and so on. And we have these statements known as guarantees, where we're essentially trying to decompose a high-level requirement and break them up into their logical implications. These are the expressions. You have logical constants, operators. You have these arithmetic comparison operators, arithmetic addition, numeric, your typical arithmetic operators, integers and real. Here's a description of the type. I won't go into this whole description, but sort of implemented. And this is a description of how type errors are reported by our ID. Likewise, unit checks, we have some sort of unit check. So we're not doing dimensional analysis, but if there is some arithmetic expression and there are units, variables with units in them, we are trying to compare the exponents aligned in the arithmetic expression. There's the semantic. So what the main takeaway is capturing requirements as different approaches. So you take the system description, component types, requirements, the variables that are part of the component type. So we ground them over all possible instances, and we have a special case where if there is no instance specified, then we take that component type to be an instance of itself. And here's the grounding of expressions. And once you ground this for different sorts of requirements, you're essentially translating into a logical formula. And so this, I'm not showing the SMT encoding for it, but if you read through this semantics, what essentially it boils down is we have an SMT translator that generates the SMT formulas for these. But and we perform, how is this SMT encoding mechanized, and what are we trying to get out of it? So here's where the main purpose of the language comes into the picture. So we're trying to find conflicting analysis, pairwise conflict analysis of requirements. Are pairs of requirements that are stating opposite behavior. Independence analysis. Is there a requirement that follows from the other? So is there some sort of redundancy in our requirement? Contingency is that we are trying to avoid the trivial tautologies or false statements. Where we're trying to say that if a requirement is true, then what's the value in having a true statement? So we need requirements to be both satisfiable and falsifiable. Global contingency is we sort of look at all the requirements as a whole and look for their completeness analysis. This is not like your completeness of logic, but rather completeness of requirements, where you're checking if there is a unique specification of the control variable for every possible monitored variable. So the way we do it is we take a bunch of requirements, we observe the monitored variable conditions, we apply the same condition and check if the control variables can take any other value than what is specified in the original requirement. So that's how we sort of catch underspecified requirements. And guarantee statements are just logical implications. So if an engineer gives us a guarantee statement, we translate that into an SMT implication and look for its validity. So here's an example of conflicting pair. So the DC-AC controller shall set certain conflict modulation to enable. This is an enum value. And the requirement, second one says that it shall set to disable. And there are a bunch of conditions. It's hard for the engineer or someone who's writing this requirement to figure out where the conflict is, but your SMT solver will do the work for you. And for us to reason, we'll have to carefully look at the condition and then find a conflicting pair. So basically, this condition holds. This is an AND condition. This is an OR condition. And because both these conditions apply for this state of the system, so we have a conflicting behavior. Here's an example of tautology. Again, you wouldn't see a requirement like this, but these were some requirements we got. So there is a enum that takes a single value, and you have a pilot shall set the landing gear to deploy when the aircraft is in final approach. So we treat this as a true statement because there's only one value that this could take. Doesn't matter what condition it is. And again, here is the incompleteness check, where we have a greater than condition for which there is a specified behavior, and there's a less than condition where there's a specified behavior. Now, if we give it to the solver, it will say that I can have a condition, and I can have a condition where it's neither on or off. And so if you throw in an equality, then you can pass your completeness. This is the use case. So hybrid electric propulsion is about to be a thing. It's not already. So you have your traditional engine which burns the fuel. Now we want to avoid burning more fuel. So you have this electric propulsion mechanism that parallelly can deliver power to the propulsion controller. And so these are the sort of models and requirements. It's like a model-based system engineering tool called Cameo, which engineers are very fond of. They use this a lot. So you have these natural language requirements model in this environment for this use case. And a bit more detail about the example that we are looking at. So we are focusing on the propulsion controller, one of the requirements, a set of requirements. And the battery is going to deliver power to the motor, AC power. And also there are these controllers, DC-DC, DC-AC controllers. And also there are power converters. Now, while these power converters are performing the power conversion, there's some heat generated. So you also have to control the heat that's being generated in the system. So you have a thermal management system as well. So you have your coolant and chiller and requirements associated with those subsystems. Now, if you put them all together, then you can make some meaningful analysis out of it. Again, this is like a summary of trace. We can capture the essence of it, the novelty aspect of it, and we can capture high-level requirements in these domains. And we can declare guarantees to check validity of your requirement decomposition. Then SMT is the backend that's powering all this. So here is an example of a multi-domain requirement capture. So we specified these domains, power, electronics, thermal. And these are your domain. We have these domain-specific equations and requirements. So if you look at DC-DC loss, the DC-DC converter loss is basically it's 1 minus efficiency and whatever the power that's being fed into it. And likewise, the DC-AC loss, because these two are connected in series, it follows from the DC-DC loss. And you can have these junction temperature calculations. Basically, it tells what's the amount of heat in terms of temperature that's being generated So you have your junction temperature calculation, which is it's taking your your coolant or your chiller system's outlet temperature, and then it's kind of using the converter loss and the thermal resistance to calculate these temperatures. And we have these guarantee statements, which are essentially trying to decompose what is involved in the calculation of these temperature ranges and um, and if they are logically valid or not. So here are basically when we run this through the tool, it will kind of statically find the dependent set of requirements based on how variables are cited. And then it will kind of compile this report as what we call as a dependent set. So this is like an over approximation of your high-level guarantee statement that you collect all these requirements and now you check them for validity. In this case, one of them is valid, one of them is invalid. In case if it's invalid, we can drill down into the counterexample. And this gives useful feedback back to the engineer so that use a formal method is a bit transparent. And along with finding the dependent set, the user who's using the system can actually trace back. There's this visual representation of this tracing requirement. Like there's a lot of repeated use of trace, and that's one reason why we kept tools name as trace. So if the user sees a problem, they can actually visually inspect how variables are defined and being some performance. So the case study, the hybrid electric case study, you could call this a toy example. And due to the performance capabilities of SMT solvers, they're pretty fast. And the feedback that we got from our hybrid electric team was a lot of the system engineers, they work in silos in their specific domain, thermal management requirements, power converter requirements. There is a real need for system integrators or system engineers to find inconsistencies, localize inconsistencies within the domain when they're putting together these systems. So all sorts of collaborative efforts with missing assumptions and miscommunication of requirements, they get hard. And there's a lot of value for it. Again, we are still in the requirements engineering phase, we not even touch the design. Now here's the model is public, the tool is not. So just to give a flavor of the language and the sort of examples that we are looking at. And this is our team's GitHub repo. This comparison, there's a lot of languages. So FRET, as FRET is right here. The FRET also does a visualization of requirements, state machines, and LTL. And it connects to a lot of backend solvers, and the range of analysis that we do is a lot. And we've kind of categorized on the sorts of requirements that these different tools cater to. And again, our friends in Loonworks are here with their Agree Annex, which we also have used. This assert is actually our internally developed tool and somewhat similar to Trace, just that the backend is we switched from interactive theorem provers to these solvers. And we've shown in support for system requirements and multi-domain requirements. Okay. So I think I had a couple of demos. Oh, yeah. Okay. I'm sorry. Yeah, I'll just do one demo. And then the second one I'll. So this is the example, a multi-domain requirement example that I was showing. So maybe I'll play this video. So it's the same example, but now it's think that was the main idea behind this demonstration. So those percentages matter, even if you nudge the value by slight, you can explore the initial design space of your problem. Then last bit of slide.
First, a round of applause. Before we have questions, let me just say, please stick around. We're going to Laura's going to announce the best paper right after we do the questions. Right? Am I correct here? Okay. So, any questions? Let's see. So I had a couple of questions. One, the connections between what you're kind of doing here with what you're doing in the Cameo model. Is it like a manual translation, or can you parse stuff at this point, or do you plan on doing some extraction from the Cameo model?
Yeah, doing extraction is definitely in plan. Right now, it's manual.
Yeah.
Yeah.
And I have a question about the units, and I probably should have read the paper closer, but there's a whole range of it, all the way from, there's sort of like I can type check basic units all the way to kind of Andrew Kennedy's inference stuff that he did all like 20 years ago. Can you, like, if I have a type that, like, meters per second, and I multiply it by 20 seconds, does it know that the type should be like meters?
It doesn't right now.
But that's some darn clever stuff that was. I mean, most of us don't do that, but that's, I guess, the clever Cambridge kid. Other questions? Oh, yes. The other Laura.
Yeah, I was wondering, you had a chart that was comparing Trace with some of the other tools. I was just there was a lot on there, so I'm trying to remember. But I was trying to figure out, like, you have a lot of these marked as not multi-domain, and I'm not familiar with all of them, but like I'm just thinking of sphere and degree. Like, they seem pretty generic. Like, why does Trace count as multi-domain but those do not?
Explicit support for categorizing equations and requirements into domains.
Okay.
And performing localized analysis.
Okay.
That's the.
And I'm guessing it's kind of because of most of us do like research, but you guys are working on like big thing like engines where you got the fan blade people and something. So I guess is that kind of what inspired that?
Yes.
Okay. Other questions? So give a final round of applause for Dave, and let me hand Laura the.
Thank you, Alwyn. Hi, everyone. So this year we have the NFM Best Paper Award that we're gonna give to the best paper. So to select the paper, we have, first of all, asked the help of the program committee that cast the vote. And we have 4 runner-up that were the 4 paper that received the best comments and notes in literature during the review process. So after the PC cast their vote, they were so good, this paper, that they were like tied, basically. So me, Aaron, and Laura evaluated the paper, evaluated all the comments, and looked at the review again, and all the comments of the program committee. And we selected the best paper, which we thought it was very well written, first of all, very original, and we also thought that it has a very good potential to be applied wide range of domains. So, drum roll. Little bit of suspense. The best paper at 4 goes to an SMT formalization of mixed precision matrix multiplication. Also, you did a very good presentation, in my opinion. So congratulations. And I want to mention that besides this beautifully crafted certificate, uh, Max will also get a money prize from Springer. Thank you, Springer, right? First day is over. Thank you for coming. Hope you enjoy the first day, and see you tomorrow at 9 for the keynote by Emina Thorlak about CEDAR. Have a good night.